and I record to the computer. They have a function you can record to the cloud, but where's the cloud, right? If the cloud disappears, all my recordings are gone. So I record to this one and save my copy. So I convert it, and everything recorded in our class activities, I put it on Blackboard. I'll show you where that is in a second. But once you zoom in, and I see you there, you're counted present. Okay, now let's go back. Let's see. How about this one? Go back more. Go too far. I'm taking too much time. I got to get through chapter 1 and 2 today. That brings up another topic. We don't have labs every time we meet. Right? So what I do is the lecture may bleed over into lab time. Okay? So you should be here. Best. Is anybody in here? I don't think anybody in here is taking the lab and not the lecture. That happens sometimes. Good. That complicates things. When I use lab time for lecture, then it's a mess. Okay, the other thing, when you're in Blackboard, let me convert back to student view. Okay, the other one that you want, well, hold on here. This NRCTC email, you can send emails to everybody in the class or individuals in the class, right? Or to me. You can't receive from here. Right? You have to log into your email account to receive emails. But you can send from here, and that makes it easier because it doesn't give you the global list of names that you have to scroll through to find everybody. It just gives you the members of your class. So I use it a lot to broadcast messages to the class. Okay, so the other thing is start here. I try to make it really simple. So if you start there, here's everything in the class. Okay, first there's the syllabus. Inside the syllabus, it's also got my schedule. You need another copy. That's another thing. Everything I hand out here is there. So if you miss getting a copy here, or you lose your copy, it's there in Blackboard. You just have to print it out. So if you pick it up here, you save on ink. But if you need to, it's there in Blackboard. So there's your syllabus. Here's your homework link. So if you click that, that takes you directly to Cengage. And then you just have to log in and you're off on homework. Cengage tech support. You know, if you're having trouble within Cengage, then you can contact them through this link. Another one is just getting started with Cengage. That one gives you some videos on how to log in, how to complete your assignments, some other things like if you have to answer questions that require drawing structures, say, or chemical equations, that type of thing. This tutorial tells you how their Chem Doodle works. Okay. So the first homework is due a long time, September 9th, right? Because we've got a Labor Day holiday stuck in there, right? That gives you an extra week. So in that time, you've got the first 2 chapters to deal with, and you've got the homework to deal with. And then when we come back after, let's see, we have a review on, well, next week. Right? Sometimes the reviews I have to use for a lecture. So we do a review, and then In this class, the week after the review, we have an exam. But this first gives you an extra week to figure out how to use Cengage and do the homework. So it gives you a little extra time. After that, then we hit the ground running. Okay, so these are tutorials from Cengage. So let's go back. You've also got breadcrumbs up here along the top. Right, they show you where you've been and you can go backwards. So if I go back here, see my there, then it takes me back to where I was. Supplemental documents, we're not worried about. Yeah, let's see what they are. Yeah, we'll deal with those later. You can explore those at your leisure. Then the class is divided into exams. You know what's covered for each exam. Like exam 1 is chapter 1 and 2. So you just click on exam 1. That shows you the PowerPoints are here, right? And the PowerPoints are in 3 different versions. Right? You've got the actual PowerPoint document. So if you have Microsoft Office, you can access the PowerPoint just as if you or me throwing it up on the screen. Okay? Or if you're some remote location and you've got your smartphone and you don't have your laptop, you can call it the PDF. The only thing about the PDF is if there are any animations in there, you won't get them on the PDF. You'll just get one little block, and it says there's supposed to be something here, but you can't see it. And then this other one is iSpring. It's written in, it's a conversion to HTML5, which is the language used for your browsers. Right? So if you click on this one, it'll pop up in your browser like that. And you can look at it. You don't need PowerPoint. I've used it sometimes when my PowerPoint was messing up. So I just go to this one, and then you can click through the slides like that. And you get your animations too. They're embedded. So you have those 3 versions. So there's chapter 1, here's chapter 2, 3 versions. Other things within each exam folder, PowerPoints. This review folder has these 2 documents that the last 2 that you picked up. 50 ways to name your compound. Yeah. And I have to show you how to name compounds before you try that one. And then getting to know your periodic table. This one, you have a blank periodic table, and you need to fill it out with these instructions. Now, the good thing about these 2 is they're extra credit. They will help you learn this stuff, but you get extra credit for doing it. Okay. I think both of them together are half an exam grade. So they're worth your effort. This one's easy to grade. So you don't have to worry about causing me extra labor. This one takes some time because it's got all these different colors, and I got to look for your symbols to be sure you got your symbols in there, you know. So it's a real pain. So I'm not complaining. It's just the facts. This one here is my version of the periodic table. I had to create this in Word because I couldn't find one that would convert so that I could edit it properly. So I said, just make one myself. Okay. But the ones that have the red borders around them, right? Those are the ones I want you to memorize, those symbols. Each one of these symbols stands for an element. Right? The others, you can memorize them if you want to. But these are the ones you need to know. This is about half of them. Right? So I cut the labor down a little bit. I've had students in the past do very well by buying or creating flashcards. And if you create your own, then you get that extra input from actually making the cards. And then you Flashman to figure it out. Let's see. We're only missing one, I think. 3, 6, 9, 12, 15. Yeah, we're missing one. Okay. I started on page 3 with exams. My dad used to say, he jumped on his horse and rode off in every direction. It's what I did. Get used to it. I digress a lot. That's why I use PowerPoints, because they bring me back on topic. Right? If I start wandering, that's how I get back to where we're supposed to be. Okay, so those extra credits are in the review folder. This other review, these documents are the way I used to do homework, only that those weren't graded. So those are there if you want extra problems to review. Right? And they've got a PDF form, which means you can fill it out right in the PDF. And there's the key, right? There's what the answers are. And then this one is very valuable. I've gone through every problem here, almost every problem, and worked them out, right? So let me just call it up and show you what it looks like. The other is a typed document, so it looks like any other document. But this one was, where is it? Here it is. There we go. Anyway, okay, so I worked out every problem. The best way to do it is if you want to use those review documents in addition to the homework. Right? There are 2 things in the homework that are graded. The mastery, when you get to an item that says mastery in Cengage for chapter 1, for instance, and the other one, end of chapter problems. Those 2, mastery and end of chapter, those are graded. The rest of it is ungraded. These are ungraded, but they're valuable. If you want to go in and do this stuff independent of Cengage, then this shows you how to work the problem. So the best way to do it is try to do it yourself first. Then if you can't figure it out yourself, how I did it will show you one way to do it. Because in chemistry, there are usually 2 or 3 different ways to solve a problem. I try to give you the easiest, quickest way, because when you're in the middle of an exam, you want to knock them out fast, right? Oh, this is important. Homework. When that due date is solid. In other words, past the due date, no credit. Okay. And the reason I do that is if you haven't finished the homework by the time the exam rolls around, it's not going to do you any good. But you can go back. I've set it up so that you can go back, even if you did finish the homework, and I hope everybody does, then you can go back for review if you want to go back and look at them again. And that's not graded, of course. That's just on your time, your effort. Attendance, let's see. Attendance is, we have a system called, I'm painting myself in a corner, drop guard. Right? The school uses drop guard, and I have to fill in attendance in drop guard. Right? We have 3 options. You're here attending, which counts. Zoom also counts. So I tell them you're attending. Another one is excused absence. Right? That's for them, excused absence. And absent. Right? So absence, obvious, right? You're not here, you're not on Zoom, we don't know where you are. But excused absence, they use in their calculations, and I assume that has federal funding and student loans and all that other garbage. Yeah. Hey.
Sorry. Just a quick announcement. If you have time, there's a presentation at 9, at 12, and at 2 for technology. So if you don't know how to use Cengage, you don't know how to use the portal for your grades and all that, or you just need a refresher on Blackboard, those are the times that I'll be doing it in room 146. And I'll teach you how to check your grades and all that.
146.
So yeah, so if you have time, just stop by real quick and ask questions about technology that we're using here. Yeah.
Okay. Everybody know where 146 is? Okay. Right over there by the door is a little floor plan, right? So you can find 146. 146 is probably, the way this thing is laid out, the hallways go this way, that way, that way, and that way, come back to where we are, right? And there are rooms in the middle. So if you just walk around that circle looking at the room doors on your left as you go, you'll find 146. Let's see, where was I? Oh, attendance. All right, in this class, for that 11%, you're either here or you're not. If you're not here, you're absent. You're not excused. It doesn't matter what happens. I mean, I understand family problems and all that stuff, small children, snow days for kids, and you got to stay home and all that, babysitters, whatever. But for grading purposes, there are no excused absences. Nobody asked me why 11%, not 10, or that's a round number. Right. Well, it's supposed to be logical. Say if you get 100% homework and 100% on all of your exams, but you never show up for class. I don't know how you do that. But let's say, hypothetically, if you don't show up in class and you get 100% on all that stuff, say you do your exams remotely, then the best you can do is 89. Right? You can't get an A without showing up. That's the logic anyway. Okay, so I use a 10-point scale. So 90 to 100 is A. 80 to 89 is B, all down the line. Most students need to get a C in this class to move forward. Okay, so D's is good in math, I guess, as far as that goes. That brings up another question. Who's doing what? Medical? Whoa, lots of them. MLT? All right. Diane warned me that I've had a bunch of MLTs. And that's fine. But I like to know my audience so I can, cover things adequately for everybody. Okay, so there's our schedule, and I've highlighted in yellow when homework and exams. Homework's due and exams on the same day. So when we have an exam, your homework's due. And then we take an exam, for instance, September 9th. We finish the exam, and then we jump right into chapter 3 and 4. Right? So the first 2 exams have 2 chapters each. Right? First one's no big deal because the first chapter is just an introduction. The second one, stoichiometry and types of chemical reactions, that gets a little more involved. So 3 and 4 is going to be intense. After that, I back off to 1 chapter each. So we go 1, 2, 3, 4, 5, 6, 7. We take them in order. Final exam, don't have one. Not enough time. The theory there is that chemistry is a cumulative science. In other words, if you don't do well in the beginning, you're not going to do well down the line. It adds up. Right? So a final exam is kind of redundant. These later exams, they require that you know what happened earlier and you master that material. Okay, so this is call attention to things. Bonus extra credit. Don't ask me for special credit. Extra product projects. If I give extra credit activities, everybody gets them, just like these two. And those are the only two, actually. So after that's done, no more extra credit. Makeup testing. If you come in and make up a test within a week, then you get, it's as if you came in on the test day and took it, right? Same consideration, same point scales, all the questions are good. Some of my exams have extra credit questions on them, right? So you have access to those too. If you wait till the second week, then any bonus questions on an exam, throw them out. You don't get them. Right? Your grade is based on the required section. If you go into the third week, forget it. By that time, we've gone too far. Just take a 0 and move on. Right? Actually, don't just take a 0. You better know that material because, like I said before, it adds up. Corrections. Sometimes I make mistakes in grading. Sometimes I make mistakes in the exam question. So if the question is not clear, maybe I didn't state it clearly enough. You know, everybody looks at a question differently. So just ask, you know, what do you mean? Or if I hand back a graded test and you think, well, wait a minute, I got that one right, didn't I? You know, let me back up. Exams. When I give an exam, what I attempt to do, and I don't know if I can with this many students, I attempt to have the test graded before you leave the class. Right, so when you hand it in, I start grading. Sometimes I don't make it all the way through, but that's my goal. And if I hand it in, if I grade it to you, I grade it for you, hand it back to you, and you start looking at it, of course, and you see something doesn't look right, then you can ask me right away, you know, about that one. If you go away and look at it later, then just make a note, you know, on the exam, recheck, and then give it back to me the next time we meet, and I'll check it, see if I made a mistake. Okay. If I did make a mistake, then I try to turn it into a learning experience. You can read exam etiquette for yourself. Just be considerate of others. I rarely have to deal with cheating. You know, most adult students are fairly trustworthy. But I do scan, you know, see if anything looks suspicious. And you may look suspicious and you're not doing anything wrong. You know, it's just, you know, your habits, right? But I may come back and check you over. Let's see. Now we're getting into the mandatory stuff. You can read that yourself. There's the appendix, and I've got screenshots and stuff to show you when you start doing your homework, you know, to help move you along. So the homework is graded by Cengage. So they just show me a value, you know, a grade for that homework assignment. And I take that and I put it in my spreadsheet. I don't use Blackboard grading system because it's not flexible enough. I use an Excel spreadsheet that I edited. I didn't create it, but I did edit it to suit me. And so that allows me to change the weighting for each of the grades. And then what I do is when we've accumulated enough grades and I've got something that's meaningful, like after the first exam, then I post that in Blackboard, right? So when you access Blackboard and look at My Grades, you should see the grades sequentially filling in. And then there'll be an overall average after you have a couple of exams, and it'll be worth averaging them and showing you what your course grade is at that time. Okay. Appendix 2 is Zooming. Right? If you log into Blackboard and go to that Zoom page, then you start up. But suppose you're not where you can access Blackboard. You can Zoom with your phone. But in order to Zoom with your phone, you need to use a different procedure. And on Appendix 2, that procedure is in number 1. The one thing that you'll need to know, in addition to these instructions, is that number in red. For this class, 765-987-127. When you zoom in that way, it will ask you for that number. And that allows you to join the correct meeting. Okay. So you don't have to use Blackboard to get in. If you use that, then you can get into the meeting. Okay, last page is the syllabus of reading. So this just says you've received the syllabus and that you're going to read it cover to cover, right? And so that you understand everything that's required of you, and then you also know what's required of me. I have to deliver this stuff. I have to, let's see, what's the acronym? This 3-letter acronym. IRA, like individual retirement account. No, it means introduce, reinforce, and assess. So those are the 3 things that I have to do. Got to introduce the material so that you understand it. Reinforce it, that's review, right? We do reviews for exams or other activities like our extra credits. And then assess, that's exams and homework. Okay, so just fill this one out and tear it off, and then leave it over there when you go. And how did I look at that? Oh, that's not part of the syllabus. Let's see if I missed anything, because I got to get into the material. Any questions? I mean, you can stop me anytime. Otherwise, I'll just keep talking. I inherited that from my father. He was a teacher too. In fact, let's see, we went back for a reunion one time where my father taught for many years. And some of the students that had graduated like 10, 15 years ago, they showed up and said, I don't remember anything that Mr. Bly said in class. I just remember that he taught all the time. So that's my legacy. Let's see if I missed anything. You should make contact with, exchange contact information with at least one other student. Okay? So that's to ensure that you have access to any changes that might take place, because certain circumstances may require that I change the schedule. Now, what I try to do is send that notification out in an email to everybody. But it's always good to have contact with another student, even a study partner. You know, the best way to learn a material is to try to teach it to somebody else. And you will learn it because they're going to challenge you. Right? I got 16 challenges right here. You're watching me to see if I make a mistake. Right? Now, what happens usually is my classes let me make my mistake and just keep on talking. They don't say anything. So eventually I get down, like I'm working a problem, I get down to the end and say, wait a minute, that's wrong. And then I have to go back and say, here's where I made my mistake. And you're sitting there, of course, giggling, having fun at my expense. I can take it. Let's see. And you want to try out your email if you haven't already, to be sure it works. Because officially, that's the only way that I'm supposed to contact my students is through New River email addresses. Okay. So I want to be sure that, I'll tell you what I'll do. I'll go into that Blackboard New River email, and I'll just send everybody a test message and ask it to tell me if you received it. Right? And then what I want you to do is just like type in received and reply. Right? So I know that everybody's connected. Right? Let's do that. You should check your email at least once a day, sometime during the day. Check your email. If you're like me and compulsive, you check it 3 or 4 times. Actually, no, I have it linked to my phone. So every time I look at my phone, there are my emails. So I'll get your email. It pops up on my phone. We'll talk about, my next item is laboratory stuff, so we'll talk about that later, once we go in the lab. And then we'll put this away. And any questions so far? I hope I didn't miss anything. So what I want to do is actually get into the topic. Now, you don't have your textbook now, probably, right? Unless you've already been into Cengage and you have it called up on your laptop. But you shouldn't absolutely need it right now because you've got the PowerPoints. So you can scribble on your PowerPoints and make notes there, and you should be in good shape. So there it is. Let's get into the material here. Be sure. Yeah. Sometimes, and we should take at least one break, right? But if we're at a point where it's not convenient to break and you just have to go take care of business, just go ahead, right? You won't hurt my feelings. Let's see here. All right, we did that already. We don't need that anymore. For that. What we do need is chapter 1. Go. Okay, can everybody see that? Let me dim the front lights, please. Okay. How about that? That's a lot better. And it's still recording pretty good without the light. Okay, start the slideshow. Chemistry. Who has a deathly fear of chemistry? That's not unusual, okay? I will try to alleviate that fear as best I can. I see chemistry as a practical science. And for medical profession and for MLTs as well, practical is the best way to go, right? You want to deal with results, right? If you're in medical profession, your patient's health is first and foremost. MLT, indirectly, should be that same goal, is the health of your patient. You want to provide good information so that the doctors, medical professionals can perform proper diagnosis, treatment, whatever. And chemistry helps you do that. Chemistry is really broad science. And I've seen one textbook calls chemistry the central science. You know, that's a little out there. But, well, if you ask a physicist, chemistry is applied physics, right? You have to ask ask a physicist. Chemistry is applied physics, right? So their heads like this. And then if you ask a chemist, biology is applied chemistry. But chemistry deals with the substances of the world and how they change from one substance to another. So you have to identify how is this substance different from that substance. And chemistry helps you do that. Now, what is matter? Right. Has anybody had high school chemistry or physics or anything like that? Okay, so you know the standard definition for matter, anything that has mass and occupies space. Right? But it wasn't until the middle 17th century we started figuring out what that matter was made of. So it's made of atoms. Sometimes those atoms combine together into molecules, right? Larger aggregates. But they're bound together in such a way that they behave as single units, okay? Individual molecules. That's not the only thing. Right? Two or more atoms joined together, acting as a unit, of course, is a molecule. But what about things like table salt? Right? There are no molecules of table salt. Right? Sodium and chlorine. But they're ions that act together. Right? So that's one that's not covered here. We will cover it, believe me. These are just examples. These are molecules, right? There's an oxygen molecule, has two oxygen atoms bound together, but it's still an element, right? Because there's only oxygen there. And hydrogen, it has two bound together in a molecule, but it's still only hydrogen, right? So elements can be molecular, or they can be atomic, that is, individual atoms. And guaranteed individual atoms, all these guys right here, noble gases. Okay, what's a chemical reaction? Well, it's a way to describe how substances change, right? And we make that description as sort of an equation, right? The left-hand side of the equation is equal to the right-hand side of the equation, right? We'll talk about that in detail later, but that's good enough for now. In other words, if you got it over here, you got to have it over there. Only it might be rearranged into different substances. Now, how do we do this? How do we study chemistry? Well, actually, we study science, not just chemistry, with a certain methodology. Science is best described as a kind of a, well, they use the term framework. It's a plan of action. That's better. Plan of action is better. It's a generalized procedure for discovering things about the natural world. Now, true scientists are always challenging what science seems to think that it knows about the universe, right? If you ever hear anyone use the phrase settled science, you can walk up to them face to face and call them a liar. Because there's no such thing as settled science, okay? You hear that a lot from global climate change alarmists. Right? That's settled science. The climate's changing, well, duh, right? It has for millions of years. I mean, changes here, changes there. But that's not settled science. I mean, their settled science is man caused it, so man has to fix it. Right? The fact of the matter is, man didn't cause it completely. And it's just one component. I'll try to stay off that course. Get up off of my soapbox. So the method that we use is called the scientific method. And it involves observation, first and foremost. You see something and you wonder why it happens. Or actually, in the beginning, just how does it happen? Why comes later. You want to know how that happens. So once you've made that observation, you form a hypothesis. That is, I think this is how it happens. You know, if you can say that, it happens because it happens this way. Then you can devise an experiment to test it. Does it really happen that way? If the experiment can change parameters and get a predictable result, then you're on the right track, right? For instance, Newton's laws, right? This is the way things happen, you know. If you push on something, it pushes back with equal force. Or if you push with a certain force, then the object is going to accelerate at a known rate, right? Things like that. And then his law of universal gravitation is another one. But when you form a hypothesis, a proposition that this is what's happening, then you can experiment and see if your hypothesis is true or false, right? A false hypothesis is not bad. What is it Edison said? He says, we understand that you failed 99 times to create and make a light bulb. No, I didn't fail. I just found 99 ways that it didn't work. I only had to find one way that it worked, right? So failure, a false hypothesis is not bad. It gives you information, right? You're on the wrong track, so maybe you need to go over here a little bit. But it works in a circle, right? Once you do your experiment, then you apply that to what your hypothesis said and say, okay, maybe I need to make more observations, change my hypothesis, and do more experiments, right? Job security. Well, eventually, you do enough of these experiments and observations that you might be able to come up with an explanation for why things happen. If you can say why something happens, then the universe opens up. And we call that a theory, right? What you get out of this is law. And all the law does is it says, when this happens, this is the result. I don't know why. Newton didn't know why, right? He didn't know why gravity worked. He called it action at a distance, right? That doesn't tell you much. But that's the best they could do in those days. It wasn't until Einstein came along that we had an idea of maybe why gravity works, right? Einstein didn't like the idea of things pulling on one another. He said, nah, you gotta have a push, right? So he came up with relativity and curved space and gravity wells and all that stuff. But he did it mathematically. You know, it's way up here. But that's a theory explaining why something happens. Then once you have the theory, you can make predictions. In other words, you can change fundamental parts and expect a certain outcome and design experiments. And you go back up here and do some of this for your experiment and refine your theory. Right. Let's see. Here we go. That's the problem. I don't look at my PowerPoints ahead of time, so you probably know where I'm going better than I do. It's on the next page. Difference between a law and a theory, right? The law just says what happens. Theory says why it happens. So we do all these experiments and we apply them to our theory. So let's get ahead of things. Back up, back up, back up. There we go. So what happens if your theory doesn't predict the way it's supposed to? You have three options. If your theory It doesn't work. What do you do? Chuck it. Start all over again. Yeah, that's the easy way out. Modify it. You know, make tweaks to it so that it works, right? Or, and this is what we do with Newton's laws. Well, this applies to laws too. But we were on theory, so I put it in terms of theory. The other thing you can do is restrict it. So, for Newton's laws, we restrict them to, I guess this is circular logic, Newtonian space. Right? Newton's laws work under certain circumstances, but when you get down very, very small or very, very large, they fall apart. Right? Black holes can't use Newton. Subatomic particles, Newton doesn't work. Right? So you restrict its application, and then you can use it, like for stuff that you see around you, even as big as cars or trucks or ships. Big stuff, rockets. It works just fine. But that's what you do if your theory doesn't work. Okay. In science, sooner or later, you're going to have to make a measurement. So we need to know what a measurement is. Science, for most scientific efforts, you need quantities, right? You got to be able to measure something, put a number to it. And when you measure something, the measurement process itself always has two particulars, two parts, a number and a unit of measure, right? The scalar. So if I say, I'm 6, what does that mean? Well, you have to put a unit of measure. You know, I'm 6 feet. I'm not actually 6 feet, I'm 5'11". But if I said 5'11", you would intuitively know what I mean. So I wanted to use something that wouldn't give it away. Right? So 5'11" means something, but the intuition is that it's 5 foot 11 inches. Right? Those measurements. So in inches, that would be what? 71 inches. Because 72 inches is 6 feet. So you always have a number and a scale, a unit. Examples, 20 grams, or the units can be compound as well, right? This number, joule seconds. Now, with modern instruments, you can make compound measurements. Right? You stick something in your instrument and it spits out a number. You don't know how it got it, but it's a measurement, right? If you make a measurement by hand, usually it's got a single unit, like grams or seconds for time. Joules, the measure of energy. Right? So you can have compound measurements, units. We'll talk about that later. Fundamental units. All right, in worldwide, nobody uses the English system. Right? Pounds, feet, inches, whatever. We use the metric system. Right? That's so everybody worldwide can talk to one another. And these are the fundamental. SI stands for, it's you know, French, they always put things backwards. System International. International system, what it means. So these units, fundamental units, are defined. And then everything else is derived from those. Right? So the fundamental unit of mass is the kilogram, right? And mass is a measure of substance, right? So mass is independent of wherever that thing is in the universe, right? It still has a kilogram of mass, whether it's on the Earth's surface, on the moon, or on the event horizon of a black hole. It's still 1 kilogram. Now, weight is a different story. That requires a gravitational field. So that mass might weigh a certain amount on the Earth's surface, but it's 1/6 of that on the moon's surface. Okay, so there's a fundamental difference there. But the mass is determined. And if you want to know, here's where Newton comes in again. Right? MA, well actually, if you want to know what it weighs, we use this. G for the acceleration of gravity, right? So if you know what G is, you know what the mass is, you know what it's going to weigh, right? The force is its weight, okay? So weight is a derived unit, whereas mass is a fundamental unit. Length is fundamental, it's the meter. Time, fundamental unit, is the second, right? Some of these were inherited. The meter and the kilogram were created, right? They were created out of whole cloth. But the second, we sort of inherited from astronomy, ancient astronomy. Right? So all we did with this one is just quantify it a little more precisely. Temperature, we created that one out of whole cloth. That's the Kelvin. Now everybody knows Fahrenheit, of course, that's what you get on the Weather Channel. But centigrade is what all scientists discuss temperature in terms of. But when you want to do any calculations, you have to convert it to Kelvin in most cases. Right? No big deal. The size of the unit for Celsius, I keep using centigrade. The size of the unit for centigrade is the same as the size of the unit for Kelvin. So all you have to do is move your 0 point. Right? And we'll talk about that again. But that's the fundamental unit. In Gen Chem 1, we won't deal with this one. Gen Chem 2, yeah. When we get to electrochemistry, you need to know what an ampere is. But we'll talk about that if you decide to take the second course. Mole, all right, we'll talk about this one in more detail too, but the mole is defined. A mole is just a number of things, right? It's a large number of things. 6.022 times 10 to the 23rd things is a mole, right? For chemistry, it could be atoms, it could be ions, it could be molecules. But technically, it could be chickens, right? Because a mole is a mole. A mole is just an amount of something. We're never going to deal with this one. Candela, we reserve that for physics. Okay, those are fundamental units. Everything else is derived from those. Now, one of the ways of deriving from those units is taking fractions or multiples of them, right? So this prefix, these prefixes give you multiples of whatever those fundamental units are, right? So I guess I ought to discuss mass, right? Anybody notice this is the abbreviation for kilogram? Before the SI was standardized, the fundamental unit was gram, 1 kilogram. Right? But it's difficult to standardize a mass that only occupies that amount of space. Right? If you're off by a certain fraction, you're way off by percentage. Right? But if you have a kilogram, you can be off by a fraction of a gram, and it still won't matter that much. Right? That's why they went to kilogram to standardize. And the kilogram is a platinum iridium cylinder and 3 bell jars, nested bell jars in inert gas in some cave over in France. Right, so if you want to standardize your kilogram, you got to go over there, take your kilogram, compare it to theirs, and this tells you what what you thought was a kilogram actually weighs. Caveat. When I say weigh, I mean mass. Right? It's a holdover from my early education. Okay, so why kilogram? Well, I told you, a kilogram is easier and less likely to be off by a large percentage error, right? So if we started with a gram, that's sort of a legacy. Then we say kilogram, then we have something big enough that we can standardize it. So this kilo in front of a gram, that's the standard unit. But kilo means 1,000 times, right? So if you have a meter instead, so for length, and you put a K in front of it, then instead of 1 meter, you have 1,000 meters. That unit of measure is 1,000 meters, right? So in Europe, driving around, well, actually the speedometer on your car is going to be calibrated into miles per hour and kilometers per hour. They all do that now. So you're traveling at a given rate, but if you measure it in miles per hour, it's one number. If you measure it in kilometers per hour, it's a different number. But you're still traveling at the same speed, right? It's just the measurement that's different, right? The physics is the same. So, which ones do you need to know? Well, let's see. Deca's 10, hectos 100, kilos, mega is 1,000,000, giga is 1,000,000,000. Right. Anybody a computer nerd in here? Sort of? So you know what megabytes are, yeah. You know what gigabytes are, terabytes are, petabytes, and now you're getting into astronomy. So you have an intuition about what that means. So you just need to know when I say mega, I mean 1,000,000 times that fundamental unit. You just put the mega in front of it. And these are the abbreviations. So a big M is mega. A big G is giga. Down here, the little k, the little h, and the little da are prefixes. If you go down to fractionals, you know, your unit needs to be small. So if you're talking about bacteria, you want to use a smaller unit, like a micrometer, micrometer. Or if you're dealing with nanotechnology, they say nano for a reason. Nanotechnology is the size of measure of those particles is on a scale of 1/1000,000th of a meter. So a nanometer is in the proper range for those small particles. Some of your clothing may have some of those particles in them now, particularly that exercise type clothing. They put nanoparticles in them. Deci is 1/10, centi is 100, milli is 1,000, micro is 1,000,000, billion, trillion, quadrillion. You don't need to know this one. You really don't need to know that one. But pico, you probably should go down to that one. Because when we start talking about the size of atoms, now you're getting down to picometers. There's another one that I'm not sure that we're going to deal with it, but I'll give it to you anyway. It has a unit of measure like that. That's an angstrom. Right? An angstrom is equal to, 1 angstrom is 10 to the minus 10 meter. Right? So notice these go in groups of 3 from here on, right? So it goes from here, 1,000 times less, 1,000 times less, 1,000. There's one stuck right in here, angstrom. I'm not purposely going to use that one but you may encounter it sometime in the future, and I just want you to know what it means. Okay, we talked about this before. Mass and weight are not synonymous, even though I use those words. Like when the instructions for your lab says weigh something to the nearest 0.01 grams. I mean, determine its mass. Right? It's just, I know some methods that are published say mass this, use mass as a verb. It just hurts my ears. Even though it's true, I mean, it's accurate. Weighing just sounds better. So just make that conversion in your brain. When I say weigh, I mean mass it. Right? Okay. Well, let's see. How are we doing on time? I have to keep my schedule. My schedule handy. Okay. I want to get through this chapter, and then we can take a break before we get to chapter 2. Uncertainty. This concept sometimes gives students trouble because we're used to hearing in popular literature and news reports, everything is this, it's not that, it's this, not that. That's lawyers talking. Lawyers like certainty because that wins cases for them. Right? In science, uncertainty is a fact of life. When you make a measurement, maybe it's what you say it is, and maybe it isn't. You know, maybe your eyes were off like this, and you got the wrong measurement. Then you got a different measurement, for example. So we have to learn how to deal with uncertainty. If you make 2 or more measurements and you want to combine them in some way, what do you do with the uncertainty of this one and that one when you put them together? Right? So we have rules to deal with that. So when we make a measurement, you should, like a switch to click in your brain. This is only an estimate of reality. Right? Who was it? Plato? Anybody remember Plato? Ancient Greece? No? Okay, never mind. He had a thought experiment. Einstein was famous for thought experiments, but Plato did them too. And there's reality, and then there's the image of reality. And think of your measurement as the image of reality. I had another professor who used to explain statistics this way. He says, it ain't necessarily so. There's a small probability that all the molecules of air in this room will migrate to that corner and will suffocate. I mean, very small probability, but it's real. It's just that you have to realize that every time you make a measurement, there is uncertainty. That's just a fact. So we have to deal with it. So when we record a number, like something like that, it's understood among all scientists that these are the certain numbers. All right, you bet your life on those numbers. This last one is the uncertain. Okay? And when you make a measurement, always estimate the last one. So if you have a measuring device that's like this, and you have something that's this long, whatever this number is, like let's say it's 1, 2, 3, 4, 5. Okay, so this 4, that's certain. The last one, the estimate, it looks like it's about halfway. That's the uncertain. So the last one is an estimate, right? That's the uncertain number. Okay, for instance, you don't need to know what a burette is yet. I'll explain it to you later. Anybody know what a burette is? No? Okay. That's okay. when you measure, what you have to understand with a burette is the numbers go from small up here to large down here. Right? Graduated cylinders the other way around, small to large this way, because you're measuring what you put in. With a burette, you're measuring what you delivered. So the small is here, so if it goes from 0 to 20, you delivered 20. That's why they're reversed. But if we take this measurement, we say there's 20, but there are 10 divisions between 20 and 21. So this would be 20, but we haven't got to 21 yet. So it's 20 point, and that's 0.1, and then about halfway in between, right? So the last one is the estimate. 0.05 milliliters is the estimate part of that number. Questions? Okay. There we go. There's the uncertain digit, that last one. Because there's no mark on there for that last digit. That's generally how you tell whether your digit is an estimate. There's no mark for it. You estimate it. Okay. The difference between accuracy and precision. So if you've had any science before, like in high school, you probably hit this topic, the difference between accuracy and precision. To determine accuracy, you need to know a true value, right? Or at least a value that's accepted by everybody that you're going to be talking to, right? True values are really hard to come by. So we generally we massage that true value into accepted value. What does everybody accept as the true value? Right? So the closer you get to that true value, the more accurate your measurement. Precision just requires that you make 2 or more attempts. And then precision is how close is your grouping. We got any Second Amendment folks here? You know what precision is when I talk about grouping of your shots. Right? You shoot at 100 yards, you're sighting in your scope, right? So you want your groupings to be very small first. So if you target, I'm not going to draw a deer, but I'm just going to draw a target. So if you hit right there, that's accurate, right? Or if you hit like that, that's accurate. But like that, that's precise because you have a tight grouping, right? That's also precise. It's a tight grouping, and it's also accurate. What about like that? It's not precise because it's not grouped, but it is accurate because the average of those values is right there. Okay, that usually spins heads around when you think of it that way. This is accurate, but not precise. This is precise and accurate. This is precise and not accurate. So if you're sighting in your scope and you get a grouping like that, then you know that your grouping's good, so your rifle's functioning properly. You just need to change your aim point. So you adjust your scope and take that group and move it over here by whatever adjustment you need. Let's see. The other one is like that. That's not accurate. That's not precise. Right? So you have 4 possibilities. So you have 2 things here: accurate, precise. It's is or not, and then that gives you 4 combinations. I think I got it. There we go. This one's got 3 of them. You left out the 4th one. This is not accurate, not precise. This is precise, not accurate. This is accurate and precise. There should be one that's accurate but not precise. And that would be if you take these and scatter them around your bullseye so that their average is on the bullseye. That's the one that's missing here. Okay. Now, we know which part of the number is certain and which is uncertain. But now we need a way to express that. And that, ooh, I must have accidentally hit a button. Significant figures. Whoa, I went a long way, didn't I? There we go. Significant figures. So this is the way of keeping track of the certainty of your numbers, or the uncertainty, as the case may be. We use significant figures because then when we combine two numbers, those significant figures for each of the numbers tells us how to deal with the result of a calculation. Okay? So, rules for counting significant figures. First, if every digit in the number is non-zero, they're all significant. Every one of them. So this one has 4 significant figures. They're all non-zero. Where's the decimal point? Right there. It's understood. Okay? Now, when we get to dealing with zeros, sometimes the presence of a decimal point or the absence of a decimal point makes a big difference. Right? So I'll point that out to you. There are 3 types of zeros in a number. Zeros that are before the non-zero numbers. Those are never significant. Never, ever. It doesn't matter where the decimal point is. These zeros are not significant. So this number only has 2 significant figures. Okay? What's next? What if we stick a 0 between 2 non-zero numbers? Like that. In that case, that 0 is significant. So this number has 4 significant figures. Okay? What's the other kind of 0? To the right. Right? We have to the left, in the middle, to the right. Zeros to the right are significant only if there's a decimal point. Right? So these 2 zeros are significant because there's a decimal right there. That 0 is not significant because there's no decimal, there's no explicit decimal. Now we understand that this is the ones, tens, hundredth position, but there's no decimal there. So that 0 is not significant. How do we make it significant if we wanted it to be significant? Put a decimal there. Now they're all 3 significant. Okay? And then there's another class of number called exact numbers. For calculation purposes, you don't have to know how many significant figures there are in these numbers. For calculation purposes, they're infinite. There are as many significant figures in these numbers as you need. Right? So if you do a calculation with an exact number, you can ignore it. It has no bearing on the outcome. And these are usually conversion factors, right? 1 inch equals 2.54 centimeters, right? Or counting numbers, right? 9 pencils, right? You don't have 9.0 pencils or 9.00 pencils. You have 9 pencils. And if you use that in a calculation, you can ignore it. You just focus on the numbers that have to follow the previous rules. Okay, exponential notation. Here's where I differ a little bit with the authors. Exponential notation is a general class in which you take a big number or a small number and you convert it to a coefficient times a power of 10. Right? So let's take an example. Say 157,302. We want to express that exponentially, right? The authors would say your coefficient would be between 1 and 10. But strictly speaking, exponential notation could be 157.302 times 10 to the third. That's an exponential notation. What they're thinking of is scientific notation, which is a subset of exponential. So scientific notation restricts your number creation to the coefficient has to be between 1 and 10. One, two, five. Okay. So if your decimal is understood to be here, and you go 1, 2, 3, 4, 5, and put it there, then you've taken those 5 positions and stored them in that power of 10. So that's 5. If you move to the left, this number gets bigger, positive. If we had something like, well, let's see, how about 0.000354, scientific notation. Now we're going to move to the right to make a number between 1 and 10, right? 3.54 times 10. Now it's negative 1, 2, 3, 4. Okay. That's scientific notation of that small number. The advantage to using scientific notation, one of the advantages is you can express very large numbers or very small numbers in a compact space. Right? If you use your calculator, it may come defaulted to standard notation. So it'll look like this or that. Right? Well, if your display only goes so far, say it only goes this far, you're going to lose those 3 digits, right? So if you set your calculator up to use scientific notation, then it will give you this number, and you won't lose any of your value. Now, how about converting backwards? Right? If you go from scientific notation to standard notation, well, we do 3, 5, 4, and here. Now that we've got a negative 4, we need to move 4 places to the left. So let's put our placeholders. So we go 1, 2, 3, 4 here. Okay. Or we take this one, 157,302, and with a positive, we need to move to the right. Right. So 1, 2, 3, 4, 5. Of course, you don't have to put that decimal there. If it's a non-zero number, it's still significant. Only if you want to keep the 0 significant do you put the decimal there. Okay? Any questions? Exponential notation. Practice, practice. That's a key word in chemistry, actually in any science. Practice. If you run across a problem, particularly in an exam, that just have a clue, that indicates one thing. Prior to the exam, you didn't work enough problems at home. Right? You need to work problems until your board's stiff. Then you can feel confident. Okay? Boredom is good. So what do we do with significant figures in math operations? Well, there are 2 rules. One has to do with multiplication, division. Multiplication and division. Multiplication division is the answer has significant figures equal to the lowest of the calculation. In other words, whatever number goes into your calculation, the least significant figure is what you apply to your answer. So you do the calculation, you let your calculator spit out as many numbers as it wants. That's fine. In this case, we put this one in, we put that one in, multiply them together, and we get this number. Now you have to round. And we use the equal to or greater than 5, you round up. Less than 5, you round down. So we take these two numbers, get that number, and we say we can only have 2 significant figures. So we have to round to this position. When you round, you find the position that you want to round to, and then you look immediately to its right. Ignore everything else, just right to the right. If that number is 5 or greater, you round up. In this case, 8 is, so you round 3 to 4. Right? You don't round 1 to this one and then round the next one to that one. You don't leapfrog from the right. Right? You're setting yourself up to create lots of errors. If you've got nothing but multiplication and division in your problem, the best thing to do, and you've got a sequence of operations, then do all the operations to the very end. Then go back and see which is the least and round the last one. That eliminates the possibility for rounding errors. Because if you do this operation and round, and then this operation and round, if each time you do the operation you round up, your error is up here, right? So save it to the end. And that gets a little complicated when we use the next set of rules. Addition and subtraction. Okay. Addition and subtraction, we set it up, you put your numbers together. There should be a line here. Add these two numbers together. You line up the decimal place, then you add them down here. Then you say, which one is the least of the decimals? Right. So you only have 2 decimal places here. So that means you round to the second decimal place. That's why this answer is 31.28. Okay. 2 different rules. Add, subtract versus multiply, divide. So let's say, what if we take 2, 3, 4, 5, and 7, 8, 0. Add those together. So 5, 2, 3. Right? I think that's right. Now, there are no decimal places there, right? How do you round this one? Well, you take the least number here. Right? There's no decimal there, so you got to go over here because that one's not significant. That's 0. So you move to the left until you find the first significant one. That means we have to round here. That means 3, 1, 3, 0. No decimal place. That gives you 3 significant figures. Okay? That's one that's not covered in the slides, so I thought I'd better show you that one. Now, what if we did this? That changes the ball game. Now, your decimal place is here. You get to keep all 4 of them. Okay? So if you see a problem that asks you how many significant figures are in the answer, and the problem involves addition, say, and multiplication, then you got to do them in the proper order, right? If there are parentheses, then of course you know what to do. Right? You do everything that's inside the parentheses first. Then you apply exponents if there are any. Then you do multiply, divide. And the last thing is add, subtract. So the add subtract rule only comes at the end. Okay? You've all had that, haven't you? Yeah, okay. Okay. Am I still recording? Yeah, recording. Gotta check. I'm supposed to have a pro account in Zoom so I can record as long as I want to. Free accounts, 40 minutes, cut you off. So I asked them, and they gave me a pro account because my classes are so long. Okay, what's next? Let's see. All right. I knew of this graduate student in marine science when I was at Louisiana State University. He had to make a measurement of some liquid to conduct an experiment. So he needed 31.4 milliliters, let's say. I'm just making that up. So he had a 100 milliliter cylinder, and he had a graduated pipette in tenths, right? So he measured out 31, and then, what did I say, 4.4? He measured out 0.4 in the graduated cylinder, put it together. Now, logically, you would think, you know, that's good. But what can he report? What can he report as the value? Oops. $31. That's all that he can report as the measured amount, right? Unless he's got a device that he can measure out the entire amount in one go, and it's calibrated to 0.4. Or, well, actually it only needs to be calibrated to this one, and then you estimate the 0.4. So the moral of that story is when you make a measurement and you make it with multiple devices, the accuracy of your measurement is restricted to the least accurate of those devices. In this case, that one restricts the accuracy of the total volume. Okay. So when you're faced with a problem, how do you solve it? Like, everybody loves word problems, don't they? Not. Because word problems are designed to confuse. Right? A lot of extraneous information in there that you don't even need. You got to pick out what you need to answer the question. So where do you start? You start with the question. That's what they're calling the goal. What is the question? If you know what the question is, then you have a fighting chance at getting the answer. If you don't know what the question is, and you just assume, then you may try to take the values from that problem and force them, you know, square pegs into round holes. I got a story about that one too. A friend of mine was a student in mechanical engineering at LSU, and he said he was amazed at how many students on an exam had studied these equations, you know, and they're given a problem, and they take those values and they just force them into the equations that they know for that chapter. He said, and the answer might come out with 32.56 billion. And it's supposed to be an expression of a length of a tube. But, you know. And I mean, think about it. They just put the number down, turn it in, get it wrong, of course. So you need to know what the question is. Plus, that begs another question, estimation. It's always a good idea to estimate what your answer should be. You don't necessarily have to estimate a value, but sometimes you can, to make sure that you're in the ballpark. but does the answer comport with reality? You know, are we dealing with something on the microscopic scale? Maybe the answer should be a microscopic value, you know, not an answer that's the size of the planet. Okay, so try to hold on to reality when you're answering questions. So once you know what the question is, you're going to devise a plan to solve the problem, right? So with the question in hand, you look at what's given in the problem. What do you know? Because you may not need all that information. So if you know what the question is, then you should be able to tell, well, I need this, 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 and this. Everything else, throw it out. And then you devise a plan to use that information to get the answer. And that's basically what I've tried to do in those problems where I show you how to do the problems, right? The worked problems. And as we proceed through the semester, I'll give you strategies for solving problems. You know, so if you recognize this problem as a certain type, then you can pull that strategy out of your pack and it gives you a fighting chance at solving the problem. One of the ways we deal in chemistry with solving problems is called dimensional analysis. And that just means keep track of your units. If you know what your units are, where you are, where you're headed, you know the units of your answer, then you know if you're on the right track to solve that problem. A lot of problems in chemistry can be solved purely by dimensional analysis without even knowing what chemistry is. So, examples. In order to do a dimensional analysis, you're going to need conversion factors, right? Converting one unit of measure into another unit of measure. And in order to get a conversion factor, all you need is an equality, an equivalence. Something is equal to something else, right? In this case, 1 foot equals 12 inches. Right? You can make a conversion factor out of that. So if you have, say, 3.2 feet, and you want to make it into inches, how do we get there? Well, in this case, you simply need something that will cancel feet and leave you with inches. Right? So if you multiply that by some value, the feet has to go down here, right? Because every number that's written without a fraction is assumed to be in the numerator. Right? This is the numerator. Right? So this has to be in the denominator in order for that to cancel. Right? So you need something up here that will give you, because this is going to retain in the answer. So 1 foot equals 12 inches. So that way, you cancel the feet, leave yourself with inches. Now, how do we know that's true? Well, let's go back to our equivalence. Well, inches. What have I just done here? Let's see. I should have made it easier than that. What's 12 times 3.2? Sometimes I can do them in my head, and sometimes my brain just will not work.
36.6.
I got 38.
Yeah, so
38.4.
yeah.
Now, this is one of those exact numbers, right? So this is the only one that matters. Now, for now, we're going to keep all three, right? Because we may want to do another calculation with it. But if we were rounding this to significant figures, right, it'd just be 2. So we'd round it to 38. But we may use it in a subsequent calculation, so we'd hang on to all of our decimals. You don't want to throw away a decimal unless you actually have to. For the final answer. Come on. Okay. So what did I just do? This is equal to that, right? That's what I'm saying it is. So what did I do to get from here to here? That has to be equal to 1. right? If those are equal, then the only thing I can multiply by that to get that is 1. So what I'm saying is that value is equal to 1. So what if I divide both sides by the same value? Have I changed it? Nope, not according to algebra. Still the same. What is this? That's equal to 1. And this is equal to whatever it is. Right? So that's my proof, that that's equal to 1. That's why it works. All conversion factors are equal to 1. So if we had a chain conversion that we need to do, say I don't want to go to inches, I actually want to go to centimeters. So once I get to inches, I need another conversion to go to centimeters. Well, 1 inch, cancel that inch, centimeters, 2.54 centimeters is 1 inch. So now I cancel inches and I lift myself to centimeters. Right? Each one of these is equal to 1. So we're chaining conversion factors by multiplying by 1s, 1, 1, 1, 1, 1. Only if we just did the actual 1, we wouldn't end up with 1 of these. 1 has to be equal to something. Okay, so as usual, I'm talking too long. Here's a chain conversion, pounds to grams. So we go pounds to kilograms first, and then kilograms to grams. Because 1,000 grams is equal to 1 kilogram. Okay? And you'll notice, let's see, I think we do it here. Yeah. We cancel units so that we end up with grams. This is something you need to be very comfortable with, because we're going to do a lot of this type of stuff, converting units. Okay, here's a practical example. Everybody's taking a road trip. What do you need to know before you go on a road trip? How much money do I need to take? Right? And one of the things you need to take money for is buying gas. Right? So you need certain values, conversion factors, to convert how far you have to go to how much money it's worth. Right? So if you estimate, say I go to Atlanta sometimes, and that's 385 miles to where I end up, something like that. So round trip, it's 770 miles. Right? So I know how far I need to go. I need to convert that 770 miles to dollars. Right? So what do I need? Well, I got to convert miles to gallons of gas. So my conversion factor is mileage. My car is miles per gallon. Right? And then I need to know what's the cost of gasoline. Right? So that's going to be an estimate. Because certain cost here, across the border into Virginia, it drops way down. And then you get into Georgia, it goes way back up. Right? So you sort of estimate. And then you add a safety factor, like 10%. But those values, those conversion factors, will get you the answer you want. Right? It's a dimensional analysis. Keep track of your units. Okay, I mentioned temperature. Kelvin is the SI unit. But we don't always have it. And we never measure temperatures in Kelvin. There's no thermometer made that measures in Kelvin. It's either measured in Fahrenheit or Celsius. Centigrade. They're synonymous. So if you measure in Celsius, it's easy to convert Celsius to Kelvin. Right? You just say Celsius, degrees Celsius, plus 273 equals, whoops, Kelvin. We don't use a degree mark for Kelvin, it's just K. But if you want to convert Fahrenheit to Kelvin, first you have to convert to Celsius. Then you convert to Kelvin. So if we want to make, let's see, if I can do this from memory. Fahrenheit is equal to 9/5 centigrade plus 32. Your book might convert this to a decimal, 1.8, same thing. I use 9/5 because it's easier to estimate in my head doing that. So, if you have a thermometer, the mercury inside the thermometer, or whatever they put in there now, is going to rise to the same place, right? It's just the measurement that's different. The physics is the same, right? So all we have to do is draw correlations between the two. So at 0 degrees, water freezes. But at 32 degrees Fahrenheit, water freezes, right? So the physics is water freezes, and it just happens at a different value for the system you're in. Okay, so I don't know if I have time to go through the story. I wish I did, but I don't think I do. So there's Kelvin. We had that 0.15, 273 is good enough for our work. You'll need that, particularly when we get to gases. And here's Fahrenheit. Yeah, I did it right. 9/5 times Celsius plus 32 is Fahrenheit. Now, what if you have Fahrenheit and you need Celsius? Well, if you know this one, you know, in a little algebra, you can come up with the other one, right? So let's convert. Let me make that one a little better. So what do we do? Well, we take this and put it over here, right? Okay. Then we solve for C. F minus 32. Let's do it this one. 5, 9. Okay. So if you know one, you know the other. You can do it that way and then plug your number in, or you can plug your number in here and then solve it. Right? Either way works. Let's see. This is interesting, but we don't have time to go through it. There is a temperature where the value for Celsius is equal to the value for Fahrenheit. So we say, okay, there's centigrade, right here, here. So we substitute, let's say, if they're going to be equal, then we just have to make these both equal. So you could make them both the x or whatever, and then solve for the x, because an equation in one unknown is solvable, right? It's equation in two or more unknowns that you can't solve with a single equation. You have to have simultaneous equations. Right? But if you've got an equation in one unknown, you can solve it. So there's what you get. You end up with, at minus 40, both systems converge at the same number. And that's the only place that they converge. Okay, what's density? I need to give you guys a break here in a second. And it should be coming up pretty soon. Just got to get density. Density. Wait a minute, did I skip anything? Density is I draw a distinction between intensity factor and capacity factor. Some authors call this intrinsic value and extrinsic value. That's two up here for me. I find these easier to deal with. Intensity factor means the value that you use to describe doesn't change for that substance, no matter how much of it you have. Right? So the density of a substance is the same if you have this much or that much. It's an intensity factor. Whereas mass is a capacity factor because the mass is different depending on how much stuff you have. Okay, that's the distinction between the two. Sometimes it's helpful to recognize the difference. Many times, an intensity factor will be a combination of units. In this case, mass per unit volume. But it doesn't always happen. An intensity factor where you only have one unit of measure is temperature. Right? The temperature of a substance is the same, as long as it's equilibrated, is the same no matter how much you have or where you look at it. Right? If you have this much at a block of ice at 0 degrees Celsius, this big, is the same temperature as a block of ice this big. Right? It's an intensity factor, but it's only a single unit of measure. Okay? But density equals mass per unit volume. So we have an equation there, right? And you can use that equation to solve for any one of those values if you know two of them, right? Like I said before, if you have an equation and one unknown, you can solve for it. So if we're calculating density, and we've measured mass and volume for that object, it's just a simple plug in here, we know the density. But what if you know the density already, and you measure its mass? Then you can find out what volume it is. Or if you measure the volume of something that you know the density of, like water, which is very well established, then you can find out what the mass is. Okay? So you can do it like that, plug in the numbers and solve, or you can solve for your unknowns. Mass equals density times volume, or volume equals mass divided by density. You can do it that way. But the unit of measure is a combination, compound unit, grams per cubic centimeter. That's the mass of the substance if you know that you have a cubic centimeter. Okay, for our purposes, matter comes in three forms: solid, liquid, gas. There are other forms of matter, but the circumstances for obtaining those forms are fairly extreme. Like on the surface of the sun, you have plasma. That's another form of matter. Or if you're in a black hole, we don't actually know what that is. I guess nobody's ever been there and come back to talk about it. But we're only interested in solid, liquid, gas. So we need to define what those forms of matter are. And it's fairly straightforward. If you have a solid, and ice is an example, the molecules are locked into position. So a solid has a definite volume and it has a definite shape. It doesn't need any type of container to hold its shape. Right? That's a solid. Definite shape, definite volume. Liquid still has a definite volume, but the molecules are able to slide past one another, which means if you put the liquid on the table, it just goes everywhere. It needs a container. So definite volume, but indefinite shape is a liquid. And then gas, those molecules are so far apart, they basically work independently. So a gas needs a container for its volume and its shape. You may have heard said that a gas assumes the volume of its container. Right? So if you put a gas into an evacuated container, then it will expand to fill the container. Okay, we did that already. So when we get two or more substances together, we can make a mixture, right? Each of the substances retains its own identity, right? But when we mix them together, they can either be homogeneous, in other words, evenly distributed throughout, so that no matter where you look, if you take that much, you've got so many molecules of one, so many molecules of the other. If you look over here, same combination, same ratio, right? That's homogeneous mixture. If they're not homogeneous, that is, where you look, you have a different ratio of the substances that you mix, you're a heterogeneous mixture. Example, homogeneous mixture, we usually think of that. In fact, another word for a homogeneous mixture is a solution. So if we mix sugar in our tea, eventually, if it's not iced ahead of time, it will go into solution pretty quick. And wherever you take a sip at the beginning, take a sip at the end, tastes the same because the concentration of sugar is the same at the beginning and the end. Assuming you don't have a lot of ice in it and ice melts and it changes. Bad example. Another homogeneous mixture, gases. You mix two gases together, you always get a homogeneous mixture, every time, without exception. So the gas that we breathe is mostly nitrogen and some oxygen and some argon, a little bit of CO2 and some other stuff. But all those gases mixed together are homogeneous every time. The reason for that is gas molecules are so far apart. You know, there's room for everybody. So you mix them together and they just go in there. You got lots of room. Homogeneous mixture. Heterogeneous mixture. Let's see, what would be a good example? Oh, my PhD is in soil science. Right? So soils, perfect example of a heterogeneous mixture. If you ever dig down into a soil profile and you look at it as you go, you see it changes. And it changes based on several things: color, moisture holding capacity, but it changes in particle size. So near the top, you'll have a certain particle size, and then around here, you get down to a certain point, and you have this layer that is very often impermeable to water. And then you have another layer below that, and eventually you get to rock. Well, around here, you get to rock pretty quick, usually. Unless you're in a river valley, like the Greenbrier. But the accumulation of those particle sizes is different. So you have a mixture of clays and silts and sands that are different. They're averaged out for a certain soil type, but if you look in the same soil type, here, there'll be different composition. That's a heterogeneous mixture. Or if you, what do they say, if you want to fill up a jar with liquids and solids, like rocks and liquid, what do you do first? Put the big ones in first, right? I think they use this in psychology for dealing with problems in your life. You deal with the big ones first. Then you put the next size in, and they fill the spaces, and then you got little spaces. So you put the next size in, and it fills spaces. Then you put the liquid in. But they're not homogeneous, right? You look in there, you can see it through the jar. You probably got more big ones over here than you do over here. Those are heterogeneous mixtures. So, homogeneous mixture. Now, what's the question? Which of the following is a homogeneous mixture? So we work from the back forwards. Which are mixtures? Right? Pure water is not a mixture. It's a pure substance. Right? Copper metal. That's not a mixture either. It's copper. It's an element. Right? So you throw those out. Then you work your way back. Now that you know these are mixtures, you work your way back to which ones are homogeneous. Well, I just told you soil is not. It's heterogeneous. How about a jar of jelly beans? Well, if your criterion is color, right, there's going to be an uneven distribution of colors in your jar of jelly beans, so that's got to be heterogeneous. Gasoline is the only homogeneous mixture in that group. Right? It's mostly octane, which is a hydrocarbon, with some other things like nonane and additives to make your engine run better. Right? Actually, to make the gas cost more. But that's a homogeneous mixture, gasoline. Okay, I'm going to have to go into a lab period to finish chapter 2, but I will give you a break as soon as we finish this one. Physical change. Physical change versus chemical change. If the change in the substance is of its form only, such as its physical form, solid, liquid, gas, or in its mixture composition, heterogeneous versus homogeneous, or different ratios of those substances, then it's a physical change. Nothing has happened to the substance itself in the process. Okay. That's a physical change. So if we boil water or freeze water, we've only changed its form. That's a physical change. And you can separate mixtures based on physical change, right? Distillation, right? If you're fermenting mash, then you turn on your burners and you distill off the alcohol. The distillation process is a physical change, right? So it comes over into your barrel with a coil of pipe and water running through it. Oh, by the way, if you want to do this, what do you do with the first so many milliliters that come off? Throw them out. Throw them out. You drink that stuff and you go blind, right? Because that's methanol. You want to keep what comes after that, the ethanol. That's the drinkable part. The first stuff that comes out is deadly. And all good moonshiners know that. Otherwise, they'll kill their clientele or make them go blind. Filtration is another way to separate, right? If you have sand suspended in water, right, you mix it up. Oh, that looks uniform. Stop mixing. It does like that quick. If you run it through a filter, you can catch the sand and let the water go through. Physical change used for separation. Chromatography is it's on the microscopic level, right? And we don't have time to talk about it. So if you look it up, any place, I mean, even Wikipedia will give you surface definition. It's good enough. Chemical change. In order for chemical change to happen, you need to change the nature of the substance. Right? So something's going on with your substance that changes its very nature. How does it behave? Good example, Bunsen burner. Everybody know what a Bunsen burner is? We use them in the lab. Take natural gas and you run it through a burner, and it controls the amount of gas that's mixed with air. Right, so you can control the size and shape and complexity of your flame. But when that happens, the natural gas is combined with air and reacts, gives off heat. The product that you get out of it is predominantly carbon dioxide and water. So you start off with natural gas, which is mostly methane. Mix it with air, which is the part you want is oxygen. So oxygen and methane makes carbon dioxide and water. You've changed substances in the process. That's a chemical change. We're going to skip these. Now you can subdivide matter based on whether it's a pure substance or a mixture, right? Pure substance can be a compound. It doesn't have to be an element, right? Like pure water. But there are no other chemicals, substances mixed in with it to be a pure substance. Mixtures, right? Can you separate those mixtures? Well, yes, if it's a mixture, you can separate them. But is it homogeneous or heterogeneous? With pure substances, it could be that the pure substance is elemental, or it could be that the substance is a compound, right? Combining two or more elements together makes a compound. And the way to separate, well, the element is composed of atoms, right? And there are ways to separate those as well. But if you want to make elements out of a compound, you need chemical methods. Over here, you can separate by physical means, but to change a compound into element, you have to use chemical methods. That is, you have to break bonds. And I know we haven't defined bonds yet, but take my word for it. Okay, that's chapter 1. We'll take a break, come back at 10:30. What I'm going to do is put out another sign-in sheet for the lab. Okay. And what we'll do is we'll stay in here so you won't have to pack up and move. To 12:20. It won't be quite as much next time. I hit you really heavy on the first day. Okay. So the syllabus for Chem 103 is the lab, and similar types of information. You'll already have a calculator, of course. There are no required textbooks or manuals. I give you hard copies at least 1 week before so that you can prepare for the lab. The best way to avoid an accident in the lab is to know what you're doing before you go in. So other things that you're going to need for your recording data, you need one of these. It's like a composition book, only it's quadrilined, right? So that you can draw graphs if you need to. Okay. And what I've done is these are available at Walmart for 97 cents. But sometimes Walmart runs out. So every time I go into Walmart, I pick up 3 or 4 or 5 or 6, however much money I've got available, and stash them, right? So I can sell them to you for $1 a piece, right? So 97 cents plus tax is what, $1.03, right? So I'm losing 3 cents on the deal. Just give me $1 and I'll give you 1. Unless you just like the thrill of going to Walmart and buying one. So we can do that whenever you're ready. You'll need one of those. And when you record things in your lab notebook, you do it in ink only, no pencil. And you can use any color you want except red. Red's mine. Now, what do you do? Well, let's talk about what else you need. So you need that. You need a lab coat, one that goes down at least to your knees. Right? Some of my students have available where they work. Some of them work in the health industry already, and they have access to disposable lab coats. And those work fine too. You know, as long as they cover you down to your knee. And then you want to wear something to cover your legs. Pants is best. And when you're in the lab, your toes have to be covered too. No open-toe sandals or shoes. Okay. Now, if you like to wear sandals everywhere else, that's fine. Just keep a pair of shoes in your car, so that when you come in the lab, you got your feet covered. This is for safety. Eye protection. We have goggles, eye protection in the lab, but these things have been used over and over and over again. They might be scratched, they might be abraded, vision may not be perfect. So if you want to, buy a pair of those. You don't have to, but if you want, you need to have a pair. You need to cover your eyes with something. Let's see, I see sunglasses. If your lenses are made of polycarbonate, then you can wear those, because mine are. They're shatter resistant. Right? So if you have polycarbonate, then you can do that. There are only occasional need for goggles. You know, if we're going to be doing some experiments that produce lots of fume and potential explosion hazards, then you need to wear goggles. But if you've already got glasses with polycarbonate lenses, and most plastic lenses these days are polycarbonate. Used to be, they weren't. You had to ask for them. Eye protection, let's see. Oh, other personal protection equipment we supply, like gloves, disposable gloves. So we'll have those. They're nitrile, right? So if you have the latex allergy, don't worry about it. We don't use latex. Some of you have brought your laptop computers. That's fine. In fact, if you had a laptop that you didn't bring today and you want, bring it to the next week to lab, because we're going to be doing a lab in the computer room. Now you can use one of their computers. That's fine. They already have Excel loaded. You need to have Excel on your laptop to do the lab. If you use one of their computers, then you'll either want to email the results of what you do that day to your account, or bring a thumb drive, stick it in there and make a copy, so that you can print it out later, because if you print from in there, they make you pay for it. It's complicated. So you take it away, print it at home, and turn it in the next week. Also, that's okay. Go to the schedule. When we have a lab scheduled and we do a lab on the date given, such as, let's go on down, say, September 16th, lab exercise 3, waters of constitution and hydration. That's going to be a formal lab report. So when you finish that lab, you take your notebook and everything that you put in it, use that to generate a formal lab report. And it's due the next time we have a lab scheduled. Right? So in this case, we skip a week. So you have 2 weeks between lab exercise 3 and 4. So when you walk in for lab exercise 4, turn in your hard copy lab report. You can also turn in your lab reports on Blackboard. Each one of the lab exercises is listed and you can print out a copy. I'll give you a hard copy, but if you lose it, like I said, everything's in Blackboard. You can print out another copy if you need it. There's also a place in there where you can attach a file. And that, if you attach it there, it'll show up in my gradebook. Right? So I'll know to go look and print a copy and do my grading thing. So sometimes we used to call them drop boxes. I don't think Blackboard calls them that, but sometimes I revert and call it a drop box. But you attach a file, and that would be, the attached file would be your formal lab report. So if you don't have your lab report finished when you walk into class, you have till midnight to turn it in. Right, so you can send it to me in Blackboard. If it gets to me before midnight, then it's not counted late, because there is a late penalty. For each day late, you lose 2% off your grade. Right, so let's say you get a perfect score of 100, but you're a week late, so you lose 14 points. You make it 86. So it pays to be on time. Let's see. So that covers when the lab report's due. When we walk in, actually midnight of the day we walk in to do a new lab exercise. Most of them are 2 weeks or more apart. Let's see, okay. Materials, we covered that. How do I grade? Lab reports are 60% of your grade. I average them all together, and they're worth 60% of your final grade. Lab skills basically is if you participate, you don't blow the place up, you don't have any safety violations. Safety violations I count in your skill score. So if you walk in with open-toed shoes, that's a safety violation. So you got to do something to cover your feet, or you can't be in the lab. And then I take your lab notebook a couple of times a year. I'll look at it pretty close to the beginning of the year to see if it's set up properly. And then later, at the end of the year, turn it in, and I'll grade it for content. So you get at least a couple of grades there. And all those together should add up to 100%. Let's see. Okay, there's a syllabus agreement on this one too. So you'll fill that out and hand it in. Just drop it over there as usual. But I do want to say a couple of words about your lab notebook. How do you fill out a lab notebook? How do you prepare a lab notebook? All right, what I'm looking for. I want your name on the cover. I want the course, just course number here, and description, like General Chemistry 1, Chem101, 103L. And the semester. That goes here. Then on the inside, first thing you do, open it up, start numbering pages with your ink. 1, 2, 3. So the right-hand pages are all odd numbers. Right? 1, 3, 5, 7 on this side, and then 2, 4, 6, 8 on the other side. Here. Okay? That's the first thing you do, all the way to the end. If you come to class, I look at it, you haven't numbered all the way to the end, you lose points. Do that first. I know it's boring, but number your pages. Odds, even. No. Odds, evens. Okay? Then reserve the first 2 pages for your table of contents. So just write table of contents here. And then when you are due to do a new experiment, you write the name of the experiment and then the page it starts on. That's all you need. Just where does it start? Then you go over to that page and you put the title. Say we go over 2 or 3 pages. Put the title and then note the page and go back here and put the page number. Then you fill in, you use your hard copy and you fill in your procedure here. What am I going to do? Okay. And to do that, write only on the right-hand side. And leave yourself space. I mean, don't bunch out everything together like that. Why? Because you want space in between your lines in case you make a mistake. You can correct it, right? And how do you make a correction in a lab notebook? You draw a line through the mistake.
So the first page table of contents, you said the second one?
Second one was extra space.
You said the second one?
Yeah, and the second one's blank too. So you write only on the right-hand side. That's because this side is an overflow page, right? You write only on this side and leave space wherever you're writing so that you can make minor corrections. But if you have to make major corrections, you may have to do like that, and there's no space to put it down here, so you do it over here. Okay. Or if you have results that you've recorded on this side, and you want to sketch in a graph, you've got a place for your graph. Okay. So, do you want to sketch a graph by hand? You can. But if you're proficient with Excel or some other graphing program, you can graph it, print it, cut out your graph, and paste it. Right? So if you do that, we need a way to tell that it's in there for good. And if somebody tampers with it, we know it's been tampered with. So what do? You paste something in here, you sign it so that your signature is both on the pasty and on the page. Right? You cross the border. So if it's removed, you know something happened to it. Okay? So you never erase, that's why it's in ink. If you make a mistake, cross through it, and make the correction. Okay? Think of the lab notebook as the record of what you have done. If you work for a company, you're going to keep a notebook. You're going to have to keep a notebook. And everything you do goes in that notebook. And that notebook is the property of the company. You have to leave it with the company if you go someplace else. That's a record of what you did, and it should be in your notebook in such a form that anybody can come in and follow your work. They can repeat your experiments if necessary. They can find where you may have made mistakes, right? So nothing personal, just business, right? It's like Godfather, nothing personal. I just want to put a bullet in his chest and one in his head. So the whole point of the lab notebook is it records what you're supposed to do first, then what you actually did. So if you go in the lab, you've got your method laid out only on this side, remember? And we make a change in the lab. Something forces you to make a change, whether it's me or circumstances. Then you make a note of that change. So this is actually what you did in the lab, okay? That's so you can come back 6 months later and repeat the experiment using just this. You don't need the hard copy, right? So if you can't take your notebook and repeat the experiment without the hard copy that I hand you, then you don't have enough information in here, okay? That's the guiding principle. This is standalone, okay? So it's standalone with the method that you did. It's standalone with the results. If there are any questions in the hard copy that you need to answer, they go in here too. You should be able to take this notebook, not the hard copy, but the notebook, and write your formal report with only this. If you can't do that, then you don't have enough information in your notebook. Okay? That's another guiding principle. Okay. So first thing you do, label your notebook, write table of contents in here. You don't have to put anything at the beginning. No, excuse me. I made a mistake, didn't I? What's the first thing you do? Number the pages, right? The boring stuff. Number the pages. 1, 2, 3, 4, 5, 6, all the way to the end. Then go back and fill in your table of contents. Go to your first experiment. Fill in what you need. Now, when you fill in the procedure, you can say, do this, do this, do this, do this, do this. Right? Instructions on what to do. When you write your report, you want to say, this is what I did. So you don't just regurgitate what's on the written report. On the hard copy. You say, this is what I actually did. So that's why in your rubric, there's, let's see, grammar. The third item down says, third person passive past tense is used. What's third person passive past tense? Well, third person, what's first person? I, me, right? Second person, you. Third person, it. It was done. So when you say, in your formal report, you say, for instance, a 100 milliliter graduated cylinder was used to measure 50 milliliters of solution. That's passive, past tense. So you do it in the past tense because it happened back then. It doesn't say do it now. Like measure blah, 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 measure blah, blah, blah. And always, please, complete sentences. All right. This is not a texting operation where you use abbreviations like LOL, OMG, and all that stuff. We use proper English in our formal lab reports. Let's see, what else? Well, okay. So the first one we're going to do is this, Introduction to Computing in Excel. So this exercise, you can make a space in here for it in your lab notebook, but since there's no formal lab report, you don't have to put it in here. I'd advise you to put it in, because if you go through here and write in here the method that you're going to do, then you'll be better prepared to perform the computer lab. Also, as you're setting up your book, you've got steps in the procedure to do. Then you would have a section for your data. If you're collecting numbers, if you're collecting observations, it's a good idea to, after you put your steps in the data section, say on the next page, create a table, or maybe 2 or 3 tables, depending on the experiment, and leaving blank spaces for numbers that you're going to collect and put in there. That's a good habit to get into, because if you have those blank spaces set up for the values and they're identified as this type of data, like the mass of blah, 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 you've got a space for it. Then if you come down here and you're putting numbers down here and you look up here and see an empty space, uh-oh, I missed something. Right? So you look and say, oh yeah, we didn't do that part of the experiment because Dr. Bly said we're skipping that today. You know, something like that. Then you can make a note, say, or cross it out. But if you have a table set up with blank spaces where data is supposed to go, then you have a way of checking yourself as you go, whether you got everything in place, whether you gathered all the information you're supposed to. Okay? And by creating a table, it also says, I know what calculations need to be done. You know, you collect the raw data, and then there's spaces down here for calculations too. Right? And then you do the calculations also in here. Leave anything out. So the rubric will tell you what needs to be in the report, and the sample report will show you what it looks like. But even this example wasn't perfect, right? So they had some mistakes. But if you do happen to create a perfect report, you have the potential to make more than 100 points, right? Because you have 1, 2, 3, 4, 5, 6, 7, 8, 9. What's 9 times 12? 108. So you can get 108 points if you get all circles on this side. If you do something like you make more than 5 spelling errors, you get 0. Or if, let's see, no, that's not right. 4 or more, you get 3 points. I don't like spelling errors, but they happen. Oh, how about conclusions and summary, right? Down there next to the bottom. Go over here. You didn't put a conclusion or summary, and those can be combined in one section. You don't have a conclusion or summary in your report. 0. You're missing a section. Actually, you get double hit there, because sections of report, if you're missing any sections, you get docked there too. Right? So this is a good thing to study when you're writing your formal report. Okay. Let's see what else I've got on my agenda. Anybody in here married and living together with one of the other classmates? Or are you all free agents? Good. Occasionally I get a class with spouses or significant others living together. I separate them into different lab groups. Because the temptation is to plagiarize, you know. Okay, I'll do the report this week, you do the report next week. And we'll just copy it. Okay, if I see that happen, it's very upsetting. So we don't have that problem in this class, right? So we'll just divvy up into, let's see, we've got 16 people, 4 groups. Would be, you know, I guess we'll get that. No, 5, 5, 1 person by themselves. That would be right. Okay, for the first lab, it won't matter because we'll all be independent in the computer room. Now, which computer room are we using? I forget the number. Let me see. I'm going to look on the map, the floor plan, and say we're going to be in 146. That's the place that Alberto was going, right? 146?
Yep.
Okay. So what you do is, go in this hallway and you go that way. You'll pass my office on the right, 129. When you get down to the next hallway, take a left. And the first room you come to on your left is an IVN room. Everybody know what IVN is? Instructional Video Network. That's where you can go in there and you interact with an instructor on some other campus. It's a way of combining small class size from different locations into one big class. So you interact through a video network. The next door on your left is 146. And you just look in there and you see rows and rows of computers, you know you're in the right place. Okay? That's where we're going to meet for lab next week. Since we'll be going from here, you know, I can remind you at that time. Or play follow the leader. Okay, so let's see. Okay, that's good. I think I covered all my points. Any questions about the lab? Okay. Let's see. Here. Get a copy of that first one. Nope, that's not where it goes. Got one more copy. Here we go. Now we can finish up chapter 2. Let's see. We got till
12:20.
yep, 12:20. I'll be pushing it, but I'll do my best. Okay, chapter 2, atoms, molecules, and ions. Come on. Oops. Retake control here. There we go. We'll breeze through this. The first attempts to explain how matter changes from one form to another was attempted by the ancient Greeks. You know, and they thought that all matter was made of 4 substances, right? Remember what those are? Air, fire, water, and earth, right? I think that's the 4. They were wrong. But then we came to a time where alchemists were involved. And alchemy is an Arabic term. You can tell because it starts with al. Al means the, or yeah, I think it means the. So the alchemists were trying to convert substances one to another, and many of them were trying to get rich at the same time, you know, make gold out of base metals. But on the way, they made some very significant discoveries. They discovered several elements. How did they know it was an element? Well, it wasn't until Robert Boyle came along, yeah, I think it was Robert Boyle, who defined what an element is. It cannot be reduced by any means, physical or chemical, into a simpler substance. So you define your element in those terms. And that's basically what they did, the alchemists. My pointer's not working. There it goes. And they also discovered several mineral acids, like hydrochloric acid, sulfuric acid were common, nitric acid. And these acids were used to prepare their substances, because many of them could be dissolved in this. So there's Robert Boyle. He was the first scientist to perform actual quantitative experiments. In other words, he made measurements with numbers. He didn't just make observations and record his results in flowery language. If you read any of the scientific reports of these days, they're long as books, and the sentences go on forever. You know, it's hard to wade through that stuff. But it's a process. We eventually got to where our reports and publications were of a standard format. And that's basically what I'm trying to do with your formal lab report. It's modeled after a referee journal publication format. Okay. And his definition of the element was just that. You know, you can't reduce it any further by chemical means. Okay, several laws came out of this early work in chemistry. One of the first ones was conservation of mass by Lavoisier. He was a Frenchman, and he's often given credit for being the father of modern chemistry. Whereas Robert Boyle did some things, Lavoisier was, I mean, that was his bread and butter, so to speak. And he said that in his law of conservation of mass, which, by the way, is just, this is what is, I can't tell you why yet. So his law said that in a chemical reaction, you don't create matter, mass, and you don't destroy mass. You have the same mass after as before. You have different substances, but the masses are all the same. And within our abilities to measure changes in mass, the law is correct, right? We know now that chemical changes, there are actual changes in mass, because now we know, based on Einstein's work, that mass and energy are interchangeable. Right? So if your chemical reaction gives off energy, like heat, had come from somewhere, and it usually comes from, well, one of two places. It comes from the energy that's contained in the bond itself, but sometimes it comes from a conversion of matter. But for chemical changes, the amount of energy released is so small, but matter is even smaller, right, because of this. Right. So a tiny bit of matter makes a huge amount of energy. So if you just have a little bit of energy come out of a reaction, it's even unmeasurable amount of matter. Right. But Lavoisier was correct insofar as we can measure. Lavoisier was a rather unfortunate fellow. He also bought from the King of France a contract, a position for collecting taxes. And you know, tax collectors make enemies. Well, he made a few enemies. Unfortunately, he was enemies with the leaders of the French Revolution. So they got even. He lost his head. Anyway, then there was Proust, who came up with this law, the definite proportions. When you have defined a compound and you've simplified it, you've purified it to its simplest form, you know it has two or more elements in it, different elements, right? So it's a compound, but you've made it a pure substance. Okay, once you have that pure substance, it always contains the exact proportion by mass of those elements, no matter what its source, right? So if you get it from a combustion process or you get it from a mining operation where you purify it, once you have that substance pure, the composition is exactly the same, no matter where it came from. That's the law of definite proportions. The proportions by mass are definite. See, at this time, there was no concept of where that mass was coming from. Right? They knew elements, yeah, but they didn't know that elements were made up of atoms. Not at this time. They just knew relationships of mass. So Dalton was an English chemist. Actually, he did more than chemistry. Anyway, he added a law of multiple proportions. So it's easy to get those two confused. Definite proportions just says, no matter where the compound comes from, the proportions by mass of the elements in that compound are always the same. The law of multiple proportions says that if you have a series of compounds that are made up of these two elements, then the proportion, if you hold one of them constant, then the proportion of the others are in whole numbers, right? So if I use, let's see, NO2, NO3, that one has a charge. But if you look at the ratios, the ratio of mass of this one to this one to this one is in, if this is 1, this one would be twice that one, and this would be 3 times that one. That's multiple proportions, okay? Now, they didn't know this relationship, right? They only knew that the ratio, if this is 1 to 1, well, if this is given the value of 1 in this compound, then if you go to this one's twice, this one's 3 times the mass. It wasn't until later that we knew why it was. This is just a law, it's not a theory. The whole number ratios of the elements is the heart of Dalton's law of multiple proportions. Now, Dalton came up with the first recognizable and useful atomic theory. He kind of borrowed this one from the Greeks. The ancient Greeks did say that every substance was made up of a single particle. In other words, it's a collection of more than one particle. They called it the atom. And in Greek, atom means not cut. That's A in front of a word means not. It's the negative. And tomos means cut. So, everybody heard of a microtome? What a microtome is? It's a device used to cut thin slices off of things before you put them under a microscope. So an atom is not cut. In other words, you can't make it any smaller. Once you keep subdividing your substance, your pure substance, keep subdividing it, you can get down to the smallest part is an atom. Okay? The mistake that the Greeks made was they said every substance was made of the same atom. And we know that's wrong now. So Dalton borrowed that idea. He said each element is made up of these indivisible particles called atoms. And that the atoms of every given element, so the atoms of neon, each atom is the same. Right? You have one atom. If you happen to divide it to where you end up with a different atom, it's going to be the same as that one anyway. Right? It's the same characteristics, chemical and physical properties. Now, remember, this is what Dalton said in his theory. I know what you're thinking. They're not all the same. Right, we'll get to that in a minute. So each of the atoms of the element are identical, and that chemical compounds are formed simply by combinations of these atoms. They bond together, they form compounds, and that's how you get different substances. Atoms recombine in different ways. Now, remember we said for oxygen, like that. 2 oxygens, that's an element. It's a diatomic element. Right? It's not a compound. To be a compound, you have to have at least 2 different atoms combined. So if we combine oxygen and hydrogen in the hydroxyl ion, that would be a compound. And we could add maybe, you know, like lye, sodium hydroxide. That's a compound. Oh, that begs the question. In that periodic table that I gave you, the one that I created, I've identified several elements in there that under standard temperature and pressure conditions exist as diatomics. Right? You need to know that, because if a word problem says react methane with oxygen, you don't react methane with oxygen to get something. Oxygen is a diatomic. At standard temperature and pressure, it's always 2 of them. Okay, that's important. Fortunately, there are just a few diatomics. Hydrogen is diatomic, so it's always H2. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So, or is that L plus that? Those are diatomics. So if we say, let's say fluorine, we mean F2. Okay. So I think I already said this one. Chemical reactions simply involve the reorganization of atoms. Now that explains conservation of mass, right? Because if all you do is rearrange the atoms, you're going to have the same number of atoms, therefore the same mass after as before. Okay, so this theory explains why that happens. And those atoms are not changed in the chemical reaction. Right? It takes nuclear reactions to change an atom. Right? We're not doing that here. This is all chemistry. All right. What other scientists came up with? Well, Gay-Lussac preceded Avogadro. Avogadro worked on Gay-Lussac's premises, and that's the way science works. We make small steps, right? That's why we publish, right? Publish your work, then everybody else reads it and says, and they have an idea based on your work. Now they're supposed to give you credit for it, right? In the literature cited at the end of their articles. This is where it came from. You're not supposed to claim that it's their work. That would be plagiarism. But if they give you credit for it and then they take your work and do the next step, then that's a valuable advance in science. And that's what Avogadro did. What did Avogadro say? Well, this is the easiest way to explain it. Avogadro said that if you have, the easiest way is to work with gases. These are spheres, 2 spheres. They're exactly the same volume, right? Exactly the same temperature, and exactly the same pressure. Right? If those are true, then we can also say that they have exactly the same number of molecules in each one. It doesn't matter what the gas is, they're equal, and N is my abbreviation for numbers of things, moles. So we have the same number of particles in this one as that one if these conditions are the same. That's what Avogadro said. That doesn't sound like much here, but it solved a whole lot of problems. Huge problems. That concept. The chemistry, after that concept was accepted and used by other chemists, chemistry itself just exploded. because now they knew how many particles of each was in a container. Before, all they knew was how much did it weigh, and it was the mass. And it's kind of hard to follow a chemical reaction with mass. You follow it with individual atoms and molecules. Okay, so I'm going to skip this for now. We're going to go to J.J. Thomson. Now we're getting into the realm of what is an atom? What is it made of? Right? So J.J. Thomson postulated, well, we knew that we could produce from elements charged particles, right? So the element itself, we were pretty sure, had to have within it positive and negative charges. Because if you could separate the negative charges from it, make this positive and you have these negatives over here, then the structure of the atom contained those particles. We just didn't know what they were. J.J. Thomson postulated that the negative particles separated in a device, the cathode ray tube, were electrons. He called them electrons. They carried the negative charge. And the positive charge we now call protons. The protons carry most of the mass of the atom. Electrons are very small, like 1,800 times less mass than a proton. So they're very small, but they have the same charge. Opposite charge, same magnitude charge, but opposite. So this is a recreation of J.J. Thomson's cathode ray tube. And he knew that the particles were charged because all he had to do was put a magnet next to this thing and the beam would bend. Right? And they knew at that time that charged particles traveling through a magnetic field would bend a certain way. They're positive, they go one way, if they're negative, they go the other way. And they knew magnets were negative, or north and south pole, so they could tell all they had to do was reverse it and they'd go the other direction. Okay, so Robert Millikan was a U.S. chemist, early 20th century, and he did these experiments with this oil drop device. And I don't have time to go into great detail, but it's fascinating to read about it. And he actually quantified the mass of an electron using calculations, that had been developed and were proven to be true. He was able to calculate the mass of an electron was minuscule, right? And he ran this device, this oil drop experiment, thousands of times, over and over. That's one way to compensate for error in measurement, and we talked about error before, is repeat over and over and over again. We call them replicates. Okay, so you replicate your experiment normally, 3, 4, 5 times, but he did it thousands of times. And that's how he was able to reach a reasonably high level of accuracy in his measurements. Because he would do his measurements, and then he would determine if, based on the aggregates, whether there were some in there that really shouldn't be there. There was some kind of mistake. Either he could account for the mistake, why it happened, or he couldn't, but it was such an outlier, throw it out. But he determined the mass of an electron. Oh. Go ahead, Sam.
Acquire a charge from air molecules ionized by an X-ray source. When distant oil drops is sprayed into the top chamber. Oil drops acquire a charge from air molecules ionized by an X-ray source. When the voltage on the charged plates is adjusted properly, the drop can be suspended between the plates. Several measurements allow determination of the charge of a single electron.
And the way the oil drop moved once you know the mass, then you know, and you know the strength of the field, and the way it's moving, you can measure it. He used a telescope to measure. Then you can calculate the mass of the electron. Retake control. There we go. So we know positive, negative charges, and we've identified the electron. Then we start getting into, well, actually, just prior to this, we identified radioactivity. You know, some elements spontaneously decay. They change into other elements, right? And in the process, they give off radiation. Well, this is a rough outline of the radiation. It can be broken down into subdivisions, right? But most radiation is either gamma ray, which has no mass. It's light, basically. High energy light, right? It's ionizing radiation. In other words, if you get hit with gammas, it's going to damage your cells, your chromosomes, right? And that's why it causes cancer. Then there are beta particles, which are basically high-speed electrons. They originate from the nucleus of an atom that's in decay. You can stop those with a sheet of paper. And then there are alpha particles. They're basically the helium nucleus. Okay. So we'll talk about that a little more. So these are three types of radiation. This one is massive. This one has virtually no mass. This one definitely has no mass, but this has very small mass. This is huge mass by comparison. Alpha particles, you can stop those with plastic, a sheet of plastic. They are really dangerous if you inhale them. Right? If you happen to inhale a radioisotope that emits alpha particles, well, the others as well, then they start doing their damage internally. That's a problem. But now they were studying radioactivity, and they knew that these things originated from the nucleus. So they were giving us clues about what the nucleus is made of, right? Because an atom, we now know, is a nucleus. And then the electrons are all out here, outside the nucleus. Most of the mass is contained in the nucleus. Now, who told us that? Ernst Rutherford did experiments on the nucleus. He wanted to know which model. See, when you have a theory, it's usually accompanied with a model. That is, something that you can visualize, you can mentally tear it apart, put it back together, see how it works. Kind of like a model battleship or a model airplane. It's not really the airplane, but it represents the airplane. That's what models do. So Ernst Rutherford did experiments, and one of his experiments was the gold foil experiment. In other words, he wanted to know what was the structure of an atom, and he had several theories that proposed models for the atom. One was called the plum pudding model. So they had identified electrons and protons. They said, okay, here's the atom. Right? It's like plum pudding. Right? The plums are scattered throughout. I mean, they just mix together. Protons and electrons. If this model were true, then when he conducted his experiment, he fired alpha particles at a thin foil of gold. He used gold because he knew that you could hammer it very thin, where it was only maybe 4 or 5 atoms thick. That's why it didn't take very much gold to cover the state capitol. They just hammered them really thin, and they laid them out on the surface. And you could probably cover the whole dome with maybe a couple of ounces of gold. Anyway, if it was the plum pudding model, then when he fired alpha particles at that, most of them, I mean, they all just go straight through, right? Because the mass was scattered around, and you maybe get some deflection like this, but most of them would be, you detect them on the other side, straight through. So that was the proposition. If he conducted this experiment, that's what he would expect with this model. If, however, the atom were a nuclear atom, where most of the mass was contained in a dense nucleus and the electrons were out here, then if an alpha particle struck the nucleus like that, it just bounced straight back, and he detected it back over here. Or if it hit off center, it would go like that, detected over there, over there. And if it went between atoms like this, it just goes straight on through. Most of them went straight on through, right? Because most of the space in an atom is empty, or it has just electrons, which have very little mass and wouldn't slow an alpha particle down. So that's what he detected, and determined that this is the proper model for the atom. So plum pudding went out the window. Just throw that theory out. There's no way to modify it and make it better. No way to restrict it and use it in certain circumstances. This is the only one that satisfied conditions. And your book gives a description of the gold foil experiment. Read it. So now we know where the protons are located. Only if we take the mass of the proton, which is most of the mass of the atom, and you can ignore the electrons, that doesn't account for all the mass in an atom. It accounts for all the charge, right? But it doesn't account for all the mass. So we needed another particle that had no charge, and that turned out to be the neutron. So now we know that atoms are made up of protons and neutrons in a dense nucleus, and electrons in this space outside the nucleus. Now the neutrons are there. I mean, they serve a purpose, right? They hold the nucleus together, right? Because what happens when you get lots of positive charges stuck together? They want to go like that, don't they? Well, the neutrons are there to keep together. And the more protons you have, the more neutrons you need. Right? So up in this region where you have smaller amounts, the ratio is 2 protons, and that's what these numbers are. They're the protons. And this is the atomic mass. So you have 2 protons and 4 nucleons. So 2 of those are protons and 2 of them are neutrons. So up in here, you generally have a 1-to-1 ratio. Same number of neutrons as protons. But as you get bigger and bigger and bigger nuclei, you need more neutrons to wrestle those protons together. But down in here, you get huge, large numbers of neutrons that are required. For instance, uranium, 92 protons, but 238 mass number. So 92 of those are protons, and the rest of them are neutrons. So you have a huge amount of neutrons required. Okay. So the nucleus is very small compared to the atom. So here, minus 13 centimeter, 10 to the minus 13 centimeter for the nucleus, and the whole atom is on the order of 10 to the minus 8 centimeters. So anybody, do you understand what I say when I say orders of magnitude? Powers of 10, right? 1 power of 10 is an order of magnitude. So the difference between 13 and 8 is 5, right? So if 5 orders of magnitude different, that's huge, right? 100,000 times difference in this space versus that space. That's why you can compress matter. I mean, even solids, if you have enough gravity, you can compress them down even further. Neutron stars are supposedly the densest objects known in the universe, well, aside from black holes. Okay, now, one thing about Dalton's atomic theory was wrong. He said that all elements in a pure substance are exactly identical atoms. Right? They're not. All you have to do, well, let me back up. What do you need to define an element? The number of protons. If you change the number of protons, you got a different element. Right? So hydrogen has 1 proton. If you change that to 2 protons, you get helium. Right? So anytime you change the number of protons, you get a different element. But we know that the elements have different mass numbers. So let's do this. There's our generic symbol for an element, right? And notice the symbol is either 1 letter, capital, or 2 letters, capital and small. Right? That's the only option you have. Either 1 letter, capital, or a capital and small letter. So I'm just going to use 1x to represent anything. There are 4 corners here, 4 positions around that element, and they're reserved for certain types of information. Okay? So if you write the symbol, we'll start with this one. This one is numbers. How many of them are there? How many atoms are there together? Right? So for your diatomics, that oxygen element has 2 atoms together in the molecule. Okay? This one is reserved for charge. So if you don't write anything up there, it's assumed to be neutral. You can write a 0 if you want. If you want to emphasize the fact that it's neutral, that's okay. That's for charge. Let's see. This one is for number of protons. Okay. This is number of atoms. If you have more than one. This is number of protons, and we abbreviate that with a Z, the Z number. Number of protons, that's the atomic number. And this is, do I have that on a slide? Yeah, A. That's the mass number. Now the mass number is simply the number of protons plus the number of neutrons. That's it, the mass number. So if we write oxygen in this form, those oxygen atoms could possibly be, well, they will always have an 8 here. If it's not 8, it's not oxygen. But it could be here a mass number of 16. Right? That represents a particular isotope of oxygen. It has 8 neutrons. If we change the number of neutrons, we still have oxygen, but we have a different mass number and a different isotope. And I think maybe 15 is another common one, like that. Now, if we're just writing the symbol for the element, you don't have to put the 2 down there. It's only when you're using it in a chemical reaction that you need to put that 2. What's another example? How about uranium? Okay, so it has to be 92, otherwise it's not uranium. And then 238 is one isotope of uranium, right? So how do you get the, well, here, 238, right? So how many neutrons do you have? (146 neutrons). Okay? Because this is the total of protons and neutrons. So subtract the protons from the total, and you get the number of neutrons. Okay? Now, if we take away 3 of these, say it's 143 neutrons, then you get uranium 235. What's so special about 235? Well, when you remove those neutrons, there's not enough of them in there to keep the nucleus stable. Right? Remember what I said? You need more neutrons when it gets bigger. Well, if you drop it to 235, that's an identified isotope of uranium, then it becomes unstable. It's radioactive. It fissions. It produces two smaller elements that are more stable. So this is a very small percentage of uranium in ore. So what you have to do is, if you're the Iranians, you get yellow cake, which is a purified form. You take that and you convert it to uranium fluoride, and you run it through a gas centrifuge at several 100,000 RPM. And that separates the more massive from the less massive, and you just gang those together, and eventually down the line, you concentrate your U-235 to the point where you can make a bomb. Okay, that's what they're after, that 235. So if you have enough 235 together, then when it splits, it also gives off a couple of neutrons, fast neutrons. And they strike more, causing it to fission, and you get a chain reaction, and Bob's your uncle. You get a bomb. If you control the neutrons, slow them down, and absorb some of them, then you can control the reaction so that you get the heat out of it, but you don't get the bomb effect. And that's what we do in some types of nuclear power reactors. Okay, so you got these four positions, and once we start doing chemical reactions in class, we'll really be only interested in these two right here. Because once you've written the element, the number of protons is fixed, right? And we're only interested in the mass number for discussion purposes. Right? So for this chapter, of course, you'll need to know that. But in the future, it won't be so important. From that point, instead of mass number, we talk about atomic mass. Don't want to get those two confused. Mass number is the non-fractional, the whole number, addition product of protons and neutrons. But the atomic mass is an empirical value that's determined, and it will have decimal values because it's a weighted average of these guys. Okay, we'll talk about that more in a minute. Okay, so let's see. Let's talk about chemical bonds. This is basically an introduction to chemical bonds. We're going to get into more detailed chemical bonds in chapter 9 and 10, I think. But this is an overall, this is a description of what type of chemical bonds there are. The covalent bond is the strongest bond. And it's the one that you will see when we're talking about molecules, that is, combinations of atoms that behave as a single unit. Okay. Those are covalently bounded, like water, H2Os. So you'll have oxygen bound to hydrogen. That's a covalent bond. Characteristic of covalent bonds. Why covalent bonds? They result from sharing electrons. In other words, you don't transfer electrons completely from one to the other. I mean, they might prefer spending time over here, but there's enough sharing going on where you get that strength of the bond from the sharing.
Halogen atoms will combine to form single bonds. Atoms combine to share electrons, forming a covalent bond. The covalent bond is often shown as a link between atoms, although it is actually a sharing of electrons. The diatomic chlorine molecules maintain their bonds even if they collide with other molecules.
Okay? So they behave as separate units when they're covalently bound. Ionic bonds result when you have positive charges and negative charges of different atoms established, and then the bonding itself is purely electrostatic. And those bonds are weaker than covalent bonds. So if we have sodium as a solid, and that's the abbreviation for solid, combined with chlorine, which is a gas. So I'll take two of these. Then you get sodium chloride, and this is a positive charge, negative charge. Right? We write them together, but they're really not bound as separate molecules. In other words, they're more in a matrix of sodium and chlorine. It'd be like sodium surrounded by chlorines, like that. Then you have some more sodiums in here. Okay, it's just a network of the positive and negative charges. This is the simplest ratio of positive and negative charges. That's how we write it. But what's happened is, if sodium is positive here, how do you get an ion? Right? Sodium is what? Where's sodium? Over here. 11 protons. So it has 11 electrons too if it's neutral. Right? So it has 11 electrons and 11 protons. Then how do you get a charge? How do you make an ion out of a neutral atom? Can't change the protons. If you change the protons, you got a different element. Right? So you have to change the electrons. Either add or subtract electrons. So in this case, we subtract an electron. Right? We've lost an electron. So now the net charge is positive 1 because we transferred an electron somewhere else. Okay? So where did it go? Chlorine is 17. So that means it has 17 electrons, 17 protons when it's neutral. But if we add an electron, 18 electrons means we have an imbalance of 1 negative charge. Right? So now, that's where the charge is. So we transferred an electron from here to here, makes this one positive, makes this one negative. Now that the transfer has been made, the electrostatic charge pulls them together. Okay, that's an ionic bond. Now we have special names. Right, these are ions, but the positive ones are called cations, and the negative ones are called anions. Okay, just have to memorize it.
Water, on the left, is a molecular substance that exists as a liquid at room temperature. Sodium chloride, on the right, is an ionic substance that forms solid crystals at room temperature. Molecular water has covalent bonds holding hydrogen atoms to oxygen atoms, but there are no bonds between molecules, so they move freely in the liquid. The ions in sodium chloride are held together by ionic bonds, which restrict motion of ions in the solid crystal.
Okay, ionic covalent. There are other types of bonds, but those are the main. There are types of bonds that occur between molecules, right? And they're much, much weaker than the covalent bonds or the ionic bonds. We'll talk about those later. Okay, let's see. All right, so Dalton's theory, now that we know that Some of his postulates in his theory are still true. Elements are made of tiny particles called atoms. Yep, that's still true. All atoms of a given element are identical. Nope, they're not identical. They behave similarly in chemical reactions. That's true. But they're not identical. That's the concept of isotopes. A given compound always has the same relative numbers and types of atoms. That's true, still true. So if we have 2 hydrogens and 1 oxygen, we have water. But if we do a different ratio, 2 hydrogens, 2 oxygens, you get hydrogen peroxide. Completely different behaviors, right? Atoms are indestructible. Well, by chemical means, that's true. Right? You can destroy an atom by nuclear means, but not by chemical means. So technically, those 2 are still true. And atoms indestructible, now we get radioactive decay, they self-destruct. Or you can put elements in a chemical reaction, bombard them with neutrons, and actually change them to different elements or isotopes of the element. Okay, periodic table. This is your best friend. It organizes all the elements that we know. And now we've filled and named them all. In other words, I slid these in here because this chart didn't have those before. So they all have names. And we've gone all the way up to 118 atomic number with our elements. There's probably some research scientist somewhere trying to make a name for himself, so he's going to find number 119 somewhere. Anyway, the organization of this chart is no accident. First of all, major division, metals versus nonmetals. See this red line right here? Well, probably should go like this. Non-metals on this side, metals on that side. So most of the elements of the periodic table are metals. Then we have groups. Sometimes we call them families. They're the verticals. This is a group or a family. They have similar chemical characteristics. These are the alkali metals, and then some of the groups have names. Alkali metals, they behave similarly. Right? Lithium, sodium, potassium, rubidium, they all behave similarly. Not exactly similar. Alkaline earths, magnesium, calcium, strontium, barium, they all behave similar. Noble gases, right? They generally don't react with anybody. They can be forced to, let's say. As you get more mass, these higher mass elements can be forced to react with others. But as a general rule, they don't want to. These are halogens, right? They all behave similarly. Fluorine, chlorine, bromine, iodine, they all behave similarly. Oxygens, these are the chalcogens, spelled with a CH. CHALCOGEN. Oxygen family, these are pnictogens. Starts with a P. P-pnictogen. And those are the only ones that have family names. The periods go this way. And it's called periodic table because if you progress atomic number from left to right, it's bigger and bigger, and you change characteristics as you go. But you go across, and you get here, and then what happens out here? Well, if you go to 37, it has characteristics that are similar to this family. So you put it over here. Does anybody have physics? You know what periodic motion means? We normally think of motion as go from here to here. Periodic motion is to go from here to there and come back to here, like a swinging pendulum. So that's why this is called a period, because we went to this end, now we got to go back and start over again. Right. So that's a period. And they're in there for a definite reason. We'll have to explain that later. But learn these general characteristics, fill out that extra credit, and rack up the points early so that if things get bad later, then you have something to fall back on. So those are periods, families. Oops, went too far. Here we go. Now, other general divisions. These are the transition metals from here to here. Right? They transition from this side to that side, for lack of a better way of describing them. These are the lanthanides, and they should, everything on this row should go right in here. Notice this goes from 57 to 72. Right? These guys fit right into that crack. We pull them out here so that we don't have to expand the chart over there. Right? Makes it more compact. And same for the actinides. Lanthanides go right after lanthanum, actinides go right after actinium. Okay, now, in a chemical reaction where you have charges developed, some of these families only have one charge possible. These guys are always +1. Alkaline metals, +1. Alkaline earths, +2. These don't make a charge. Halogens are always -1. You know, most of the time. Fluorine, yeah. If you look on the, let's see, is that period? Periodic chart. You'll notice in the periodic chart I gave you that there are multiple charges available. In general, at least for now, learn that those are +1, +2, -1, -2, and -3, and then it gets kind of squirrely here. But definitely -1, -2, -3 in ionic compounds. Another one you want to know is aluminum, which is always +3. Okay. Naming compounds. Okay, we need to know how to name compounds. We're going to start with binary compounds. That is, you have only 2 elements, or actually 2 groups. Sometimes they're elements, sometimes they're groups that act like elements. But they're binaries. So you usually have a cation listed first, followed by an anion. So you put the positive one first, negative one second. These could be ionic, they could be covalent. We use the same convention for both of them, even though you have to understand that covalents are not charged. If the binary is ionic, then it will be a combination of a metal and a nonmetal, always. So you have a metal from over here, like potassium, and a nonmetal from over here, like chlorine. And you make potassium chloride, which is light salt. If you have a nonmetal and a nonmetal, like 2 of these together, for instance, carbon and 2 oxygens, carbon dioxide, that is a binary covalent compound. Okay, they're always 2 nonmetals to make binary covalent compounds. Now we need to go through the rules. All right, 3 types. Type 1, the binary ionic compound. Cation is always first, anion second. When you name the compound, the cation is simply the name of the element. So in our example, potassium chloride, potassium, you say potassium. So KCl would be potassium. And then the second one, the anion, you take the name and change the ending to "ide." Okay. That brings up another point. We mentioned that these symbols were either single letters or a capital and small. Most of them bear resemblance to the English name for the compound. Some of them don't. Some of them are derived from the Latin. Potassium is one of them. Okay, there's no K in potassium. That's because the Latin for potassium is kalium with a K. There are others like that. Sodium, natrium. Right? Let's see, where's another good one? Well, lead, right? There's no PB in lead. The Latin for lead is plumbo.
Not AG gold.
Yeah, silver. Plumbum is Latin for heavy. And Ag is argentum, which is silver. Gold is aurum. Right? There's several of them in there. Stannum is tin. So those you just have to memorize. Right? And that handout that I gave you shows you the ones that I want you to memorize. About half of them. And there should be, I think most of those halves include, well, iron, right? Ferrum, it's Latin for iron. Okay, I digress again. Okay, so that's type 1 compound is the way you name this. So you should be able to go backwards and forwards. If you're given this name, you should be able to write that compound, right? Potassium, from here, always has a +1 charge. Right? So you would write like this. Chlorine is a halogen. It always has a -1 charge. So what's the smallest numbers of each one that will give you a stable compound? Not a stable, but what's the smallest ratio, right? 1 to 1, right? 1 plus, 1 minus. That's it. That's your compound, KCl. If we did something like calcium, we'll stick with chloride. How would you write that one? Well, the symbol for calcium, right? Symbol for chlorine. It's always a -1, but calcium is an alkaline earth. It's always +2. So how do we balance the charges there? We need 2 chlorines. So calcium chloride is like that. You got to be able to write those compounds, otherwise your chemical reactions will never work. The whole purpose of naming conventions is so that you can unambiguously go one direction or the other. Go this way, go that way. Right? No mistake. That's the whole point behind nomenclature. Okay. Type 1, type 1. Examples. Type 2s. Type 2s are also metal, non-metal, right? This is metal, non-metal, but the type 2s, the metal is from a place in the periodic table, and the metal could possibly have more than one charge, right? And most of the time, those are the transition metals. Right? They can have multiple charges. So what you have to do is come up with a convention where you can identify in the name what the charge is. So we do that with Roman numerals. Right? So for instance, if we have iron, chlorine, that doesn't tell you much. I mean, because iron could possibly have a +2 or a +3 charge. Let's say it's a +3 charge, right? Chlorine, we know, is -1, right? So we need 3 of those, don't we? So how do we name it? Well, we don't have to use the Latin name anymore. Back when I was getting started, you had to learn the Latin name and apply it with certain other conventions. We don't have to do that anymore. So we just say iron, chloride, and then in here, we specify the charge on the iron because it could be variable. Say 1, 2, 3. That's the charge on iron. Now, unambiguously, we have identified the charge on the iron. Chloride's always the same. We could write the compound from that name without making a mistake. Okay? And just to keep things simple, if it's a transition metal, put the charge in. There are a couple of elements in here that only have one charge. Silver, for instance, it's always +1. But if we want to keep it simple, just say if it's a transition metal, write the charge, and it won't be wrong. In fact, it won't be wrong if you do it the other way too. So if you choose not to write the charge for silver in a compound, it's still right. You can use the type 1 convention. Okay. Type 3. So type 1 and type 2 are both metal, non-metal. Type 3 is non-metal, non-metal. Oops. I'll come back to the polyatomics.
To work out the
Let's do 3. I want to keep our train of thought going. Type 3s, non-metal, non-metal. With type 3s, since non-metal, non-metal is invariably covalent, there are no charges involved. So you can't tell what the combination of the two nonmetals is. But we treat them as binary ionic compounds for naming purposes. In other words, it's as if it were a cation-anion arrangement. So if we had nitrogen and oxygen together, well, we had 2 nitrogens, then we would have dinitrogen. You say how many there are? Monoxide. Okay? You just say how many there are. That's it. No charge involved. Except if we had this one, we don't say mononitrogen. It just doesn't flow right. Chemistry still has some aesthetic qualities that we cling to. So we would say nitrogen, and it's understood to be only one, nitrogen dioxide. Okay? You always say mono in the second part. So we're treating the nitrogen as if it were a cation and the oxygen as if it were an anion. Generally speaking, the one on the left is treated like a cation because it's closer to the metals. The one on the right is treated like an anion. Now, dinitrogen monoxide is the proper name by convention laid out by this organization, IUPAC, International Union of Pure and Applied Chemists. They set the rules for naming compounds. These namings, all organic compounds, which are, they fill this room with those, so many of them. But they set the convention for naming compounds, among other things. But there are trivial names that are associated. They're sort of historical legacy. Dinitrogen monoxide, you may have had this before. In the dentist chair, nitrous oxide, laughing gas. This one doesn't have a trivial name. But the systematic name, the SI name, by IUPAC, is this one and that one. Okay. All right, we're out of time. Let's see. What have we not done? Oh, polyatomic ions. I have a list. Did I give you a list of polyatomics? There should be a list of polyatomics in your book, your electronic book. The polyatomic ions, all but one, are anions. Okay? For instance, nitrate. They behave as individual entities in a compound. So if we combine that with sodium, which is +1 charge, sodium nitrate, right? Saltpeter. The covalent bonds in here are so strong that this ion acts as a single unit. Right? There's only one positively charged polyatomic ion that we're dealing with, and that's ammonium. Okay, the rest of them are all negative charge. Let's see. All right. I didn't get around to acids either. Shoot. Ran out of time. All right, so next time we meet, let's see, is it next week or is that Labor Day?
No, Labor Day.
So we will meet next week for review. All right. So study this stuff. I'm going to try to figure out what's wrong with that Cengage. And finish out the chapter on naming acids. Okay, actually acids and bases. And we'll talk about those next week if you have any questions about it. And we'll work problems. Okay, so assuming you get into the homework, start working the homework, make a note of any problems you have doing the homework so that we can iron those out before the exam. Okay, and when you do the homework problems, I've given you several attempts, right? So if you get it wrong, it'll give you a hint as to what you did wrong, and you go back and try it again. Okay. This is the first time I've used homework, graded homework. So I'm in the learning process too. Okay, I guess that's it. Let me shut this thing off so it can be compiling.
Do you want the safety provision?
Yeah. Yeah, just leave it here or over there by the sign-in sheet. Let's see.